Hello, everyone. So, working on implish today. As you can see, we now have a logo, or I have a logo. Yes, we have a logo if you're part of the community. So that's an imp. It's its eyes and its little tusks. You can see form the assignment operator, which will be used in implish. And then his body is a little semicolon, and his arms or his hands make little brackets. I thought that was a nice little. I just thought that was a cute little way of making a mascot. Some imperative symbology there. So anyway, that's I don't know what his name is yet, but or her name is, its name is, but that's the implish imp, and there we go. All right, so today talking about parsing. So let's get back to where hello, where I was before. So I have, so we've got like this very small little REPL here. We've got the core types and parts of speech and whatnot. And then we've got a symbol table. It's so simple that maybe might even be thrown away. I think symbol actually does most of this in JavaScript, bootstrapping in JavaScript. We've got a tree builder where with the basic operations emit an item into the tree and then create a new node, and then you're done with that node. So go back to the parent node. And then we have the reader, and the reader is a little complicated, but it reads like the basic syntax. Actually, I'd say it's actually not that complicated. It reads the syntax that looks like, well, I guess what would be in the tests. So everything in here, this is syntax. So the word nil is a symbol inside of two brackets, and then the second pass gives some meaning to that symbol. And right here we have something that says like echo 2 + 2. And I'm actually going to take this out of this interpreter and raise it up into the, like, so the JavaScript part is no longer going to handle this. And instead we're going to handle a different syntax that looks like this. Echo 2. And then instead of 2 + 2, instead of infix notation, we're going to have another one of these, and then 2, and then 2. And this is what I call projection syntax. So in K, one of the languages that we're using, that I'm using as inspiration, you can have a function like, foo, and then you say A, B, C, or its arguments. So maybe 1, 2, 3 or whatever. 1, 2, banana. And so you can see, like, in fact, this can even be like 3, 4, 5. So you can see that you're separating what K calls a vector, so a single expression. Any expression can go in here, and then, but like this is a single token in K. So this has 3 arguments, and so if you have 3 arguments to your function, then these would be filled in. Obviously, this is just how you call a function. But if you omit one of these things, so now you have a function. So you start with, say, who is, A, B, C, A plus B plus C or whatever. And then, so it's, whatever. Or whatever. We'll say A plus B reshape C. A comma B reshape C. Except I don't think that's, is that K? I don't know. It's not. It's A plus B take of C, but you can't. So we'll use a JSON tag, whatever. Doesn't matter. That's not K, but anyway, the point is that you use all these arguments, but now we have, something like that. Oh, sorry, right. And the whole point was that we're going to leave out this argument. So this becomes a new function. So it takes this function right here, and it appends 1 and banana, and it gives you back a new function, foo prime or whatever, that just takes 1 argument, right? So it just takes B. So it's partial application, and unlike something like Haskell where you have where like juxtaposing two tokens is function application. In K, juxtaposing two function names tends to be a verb and a noun would be function application, and it would create one of these projections. But you could also use this syntax to like fill in just the the third or the second or whatever instead of just the first. Anyway, so this is called projection in K, and if you completely fill in the thing, well, you project it all the way down to a scalar. So it's like you have a 3D. The word projection, you have points in 3D. You're projecting them down onto a 2D plane. That's called projection. You're losing an axis. You're losing a degree of freedom there by filling it in with a value, and then or mapping it down to something else. So, this is just part of the K syntax. But it occurred to me that I might need this. So because implish has the problem where you say, well, like where it said echo 2 plus 2. Let's say you want to say add or like multiply two things. So say mul is x times y, right? And it infers that this is two parameters x and y. So then if you want to say mul 1 2, you should be able to do that, except this is one token. So how do you put the next token in there? And so the answer is that you can use this, because if you have a verb here like ID, identifier, ID of 2, right? Well, mul will reach ahead and say, okay, I've got a noun here. And then it reaches ahead and says, oh, I've got a verb here, but I'm going to apply that verb to the noun, and then you get back a noun. Right, because I'm looking for a noun, so I need to apply the verb. I didn't, basically. And so that would do that. So this is the ID symbol. The symbol is actually ID in implish, and also in K. It returns whatever's on the right-hand side of it. So actually, this phrase in K returns 2. So anyway, that's the idea. Is that we're gonna have mul 1 times, but I don't know. So you can say that, and that's going to work, but it's getting complicated. And the reason this works, like this is not a magical punctuation symbol. This is just something that breaks up the 1 and the 2. You often wind up using the same kind of concept in J, where you use one of these brackets, right, which are both identity symbols. Anyway, that's the idea. But this is complicated to parse, and that's fine. I'm going to pay that price. I'm going to make that happen. I think it might actually happen right now, because I think it doesn't happen right now. You can do like a monad, like a single, like you can say print. To if this were defined, you would say print that, and that would work just fine. But you can't yet handle the second argument. It doesn't yet know how to combine the second, to see what to do when it sees a verb in the second place. But I'm going to get there. But I don't want to do it in JavaScript, because I found that as I'm working through this, the code is getting more and more complicated, and I want to keep it simple. I want to keep the JavaScript code simple so that I can push I can use the language I want to make to express the thing I want to express, right? Rather than try and implement it in JavaScript, I'm going to just do something very, very simple. And so I'm going to do just fully expanded code here. So like even this would not be allowed. This is going to become in the new, not the new syntax, but like you will be able to do this anyway, right? Which is you'll say mul. I guess it would be projections. So you start with this, and you're going to use the symbol mul, or I don't know, maybe you don't even need this. Maybe you don't need to quote it or not. I'm not sure. And we're going to assign mul, and so the left argument is actually probably will be this now. Okay. So yeah, this is implish now. And then the right argument is going to be this, x times y. But even that is not right because, so this is a valid, I guess this is valid in the projection syntax. Everything is going to be a container that may or may not have something in front of it. This is going to work. And then we'll say x comma y, something like that. So this would be the fully expanded version of it, which is ugly. I don't like it. But this is like the complete parse tree. And that way, every symbol, like even this would translate, and this isn't real XML, but you would translate this into, like this. It's hard because it's not, it's not XML syntax, but maybe we could call it like list. Yeah, maybe like imp list, and then tag or something like that equals this, right? And then inside of it, well, you got like imp sim or something like that. Symbol. Yeah, that's mul or something like that. Whoa. Pressed the wrong key there. Anyway, so that's kind of what I'm getting at. This is like the internal representation, and I do want to actually print out XML like that for debugging this parser when I do tests. But like right now, all I want to do is parse something like this, and I'm going to get just enough of this working to bootstrap the rest of it. So like the core interpreter is going to be written in that syntax, which I think is good because this is very much like the way the very first paper about Lisp was written. Something about programming with recursive functions, part 1, or something like that. I don't remember what it's called, but it was a paper, and it like lists out the axioms of Lisp, and it builds it up from a little syntax like this, a little meta interpreter, and then it becomes self-hosting, and that's kind of what I'm shooting for anyway. So this is just enough. This JavaScript code should be just enough to get it self-hosting, and that's all I want to do. And then I'll start building the real language on top of that in the self-hosting interpreter. That's the goal. Okay, that's enough rambling for now. So that was 15 minutes of rambling. Okay, so let's... What is the actual step that I do here? I don't know. Let's find out. So... I guess... Well, first of all, I want to use this in Emacs because it knows how to handle the holding and whatnot. But I guess so the first test is to undo this. So this is going to be exactly the same. I think this is the same. This is not really a projection syntax, but it's one expression followed by another expression, so maybe that's fine. We'll see. All right, echo hello. This is going to become echo with a, I'll revert because I just changed. Come on. Oh. All right, so we're going to change this to echo hello, and this test format is highly redundant, so sorry. And I believe this is not going to fail. So let's call this to do, and let's see if it happens. So in that directory, first of all, just make sure everything's checked in. Everything is checked in. It's all junk except for, or not junk, but stuff I'm checking in yet, except for this. And so, which is what I just changed. So let's say Tenko test. All right, and that failed. The test hello failed, which is this test right here, and it failed by printing out echo hello rather than hello. Because it doesn't have the space in here, and the interpreter is expecting a space. So let's add that rule. Actually, you know what? I want to make a copy of that test. Because the old test presumably still works, and what I'm going to do is add the rule. All right, so we'll call this hello dot implish, or what's the word? It's Polish notation, but applicative. I don't know. Okay, so that works, but this does not work. Hello dot, and this would be called projection. That fails. And so for every one of these, I'm going to go through and add a fully projected form. One of these things, so test whatever. So hello projection failed. So hello echo hello. All right, so we add this to the interpreter. We don't take away the old thing until we get the new thing working, and so on. All right, so what did we do? Well, it did parse it correctly. So now we just have to go to imp eval. And how does this work? So it's getting really complicated. This is why I wanted to not do it this way. Okay, so part of it's complicated because I don't know what the design is, and so I keep making little things that probably I shouldn't be making. But we have echo. So so what's happening right now is it sees this as a list. And the list has an opener, which is this echo bracket, and then this. And it's just evaluating everything inside of it. I bet, I'm curious now, I bet if we did this way, and we said, so I'll make a copy of this one as well. I'm not sure it's going to work. I think it's going to work. If we say echo 2 plus 2, add projection. Oh, I screwed that up, didn't I? Echo 2 plus 2. That's the old way, that works. But now if we do it this way, and don't do, keep that there. Echo 2 plus 2. We'll do that in a second. But I think if we do it like this, that it's gonna. I would expect this to print out echo 4. Right now, that's what I'm expecting. I understand. Yeah, it did. Okay. So because it says to evaluate that, so it is evaluating the list, and that's how it evaluates the list. And so what I need here is a test right here at this line that says, okay, if, all right, so the A is gonna, this is tag attribute value. If A dot, if A open is equal to, how about say if A open I want to match this. I want to say I want to match basically anything, and then at the end it would either be this, no, or this. One of those three openers. How do you, what's the infix notation for matching regex in JavaScript regex match infix? Oh, you say dot test. And of course, this has to be in here. A.open. Except I don't want that. I want match. Because I want to match this and then this. If M, then we're in projection syntax. Else, and we'll do something here, and then we'll say else, and then we do whatever we did before, which is this. Let me just test this here. So load or something. All right, so if I say so the tag is echo, and then let M equals, and then I'll put in exactly what I just typed, make sure it works. Match is not a function. Matches. Let's look at the docs. I don't like that JavaScript is not discoverable like this. You ought to be able to press this and say P, and it should show you. Oh, it does it? No. Right, so we say Rx equals this, and you can say Rx dot test. Okay, so Rx dot, that's what I wanted to see. Exec, I always forget it's exec. So Rx exec tag, the M equals Rx exec tag. MM. Right. I shouldn't use the word let in the REPL. That's terrible. All right. So tag equals echo. And that was a dumb way to do things. What? Yeah, there's a match. You can't see it. It says right here, match. Oh, string method has match. All right, so it's tag match, and then this. That works. But why can't I say that works? That works. That works. What did I do wrong? How is that different from what? Oh, because it added this extra end back here, and then yeah, I didn't do that. The editor added that, and I didn't see it. Okay, this is what I meant to type, and I didn't realize this extra bracket was there. Okay, yeah. So this bracket introduces like the character class, and then this bracket is one of the characters in the class. All of these opening brackets. It's a really ugly irregular expression, but there you go. Okay. So there we go. Oh, but not echo. Just anything. But not nothing. So any so basically this is a normal list which we will use a val list on, but this is a list that we will project on. And then the idea is that this is for data. So I want to make what I'm leading up to is I'm going to make a grammar right here. So you'll be able to say like you'll be able to make a data structure. So grammar, and you'll say well, or I guess so if the rule is like a where's my grammar? I threw it away, didn't I? When we get to it, we'll say like so it's like program is either going to be one of these things. So the rule is like you want to write like program is going to be like it's going to be okay, or if then, or whatever, or while, or yeah, while, or for, or assignment, and so on. And so then we would put here in alternatives, right? So this will be this character right here will be and this character right here will be, but I guess we want curlies, right? These will be tags as if they were XML tags or whatever. So any character without a space before it or without a space after it, followed by or and then a bracket or brace or parentheses or whatever, creates a thing, creates a new. What am I trying to say? A new node in the data structure. So spaces are, we can have the spaces, but we need this. All right, so then this would be like, okay, if then while for, and maybe we don't even need this. Maybe we don't even need this. The idea is that this projection syntax is like what I think of as a two-dimensional syntax, in that it has, it's lists of tokens or whatever. So these can be symbols separated by this. And in fact, maybe we could even say this. I don't know, because the two separators are going to be these two things. So either one of those act as separators, and I think that is going to be okay. I kind of like it like this, though. I don't know. Maybe we just do it like this. Something like that. Except it wouldn't be this, would it? It would be many of these. And then many of these, right? And so this is really ugly. But eventually we'll have like a nice syntax. You'll write it like this, right? Well, probably we'll write it like this: item star, and then item would be something like this, just to keep it simple. I don't know, whatever. All right, I'm off topic. Point is that we need to know what the trailing character is, because this is a function application and this is data. Something like that. Actually, instead of for readability, rather than like this, we'll probably say the word alt. Oops, alt. And instead of this, we'll probably say sequence. And yeah, I have like names for all of them already made that I use all the time. But we'll get there, and probably I hope to get there tonight. I don't know if it's going to happen. I'm going way too slow. I'm rambling about all this stuff. Okay, so projection syntax. So if we're going to do this, then we're going to switch based on, yes. So match 0 would be the whole thing. Match 2 would be the second, so switch. Yeah, exactly. And so this is going to be like project. Yeah. And this is going to be, I don't know yet. I don't know what this is going to be yet. So to say, let's do what this one does, which passes it through completely unchanged. And then this one is, we'll do this all for the same. We'll do this all right now. Let's leave this here, and then let's just validate that this actually works. This should continue to say echo 4. It shouldn't have broken. Yeah, it did. Okay. So now we're going to change this. So in this particular case, we'll change this to this. So the sim is M1, and then that, and then now let's say, what does project mean? object of function. What am I pausing for? I'm pausing because, as I said, this is a two-dimensional syntax. And what I mean by that is, like, you think normally when you're parsing something, you can parse binary formats and this doesn't apply. But if you're parsing a text file, like a text file from the computer's point of view is a one-dimensional string of characters, but from our point of view, we edit it in a text editor and we see a two-dimensional display. We see lines, a ragged array of lines, a ragged array of arrays, right? So a two-dimensional array where the first array, one line per, the first array is an array of lines, and the lines are of different lengths, so they're ragged. In this case, we're looking, if you look at a file, we parse the characters, and now we have like a list of tokens, and it's not really two-dimensional. It's a many. It could be as dimensional as you want. It's a tree, but generally speaking, the end of a line works something like a separator, right? Unless we've opened a bracket or something. Well, even then. What am I trying to say? What I want to do is I want to break this up into lists. All right, so X's is what? It's a list of symbols, including separators. So I want to say is like args equals let args equals this, and then arg equals this, like the current arg that we're looking at. And then for x for x of x's, we're just going to parse this. We're going to separate it based on separators. Yeah. That's perfect. Thank you. You know exactly what I was thinking of, Copilot. Except this should be and then at the end, yeah, that's it. Arg, push the last arg. Now, but this really is a list. So we need to make a list. And we don't really have a constructor for that yet. I'm going to add one. I'm going to say like imp.list. At the top, I said import imp. Import this as imp from imp core. And I'm going to start using that syntax now. Where'd I go? So come back here. So rather than this, we'll say imp.list and arg equals imp.list. And we're going to make a new thing called an imp list. So export class imp list. Well, I don't know if I want to wrap that. I don't know if I want to do that yet. So I'm just going to say, I'm going to do it like export function list, which is, okay, so that's going to return, yes, this exactly. Oh, right, open and close. Open and close. And so that will just be this. And then, yeah, that's fine. That's fine. That's fine. Yeah, fine, but okay, whatever. You want to do make some more? I don't need that. Oh, well, I mean, yeah, you could make that a step. You know what I'm gonna do right now? I'm gonna stash everything I'm working on. I'm gonna make this change. Git stash. Then go test. I'm at a situation where I have more tests that I have aspirational tests in my test suite. The whole point of my test system is that you can separate them, but it involves a database, and I don't have the whatever. You have to publish it to do that right now. So, what am I going to do? I'm just going to make this small change right here, the thing that I just did, which is this. And then everywhere that I construct these types, which is probably mostly in the parser, in the reader, import star as imp from that same file, impcore.mjs. So here we're going to say imp.sep x. And instead of this, do parseInt. So imp.int. Imp.string. And this is cutting off the quotation marks because it matched something in quotation marks. Oops, extra one. Multi-line strings. that didn't work for whatever reason. And then here, so anything that's not the end bracket, then we're going to emit a symbol. And so imp.sim, and it looks like I already have a sim table here, so maybe I should only have one sim table. I don't know. But I'll leave that alone, and rather than doing the word symbol here, I'll just say X. All right, so these are all very simple. And anywhere I see t.list x that, what is x? What we expect. All right, so then for tree, we'll just pass in the attributes because that's the only one that actually uses attributes at the moment. And I'm going to use PyCharm. I have this loaded in PyCharm. The whole point is because it catches little errors from. All right, so if we open up imp command, all these little things we don't care about that. I'll clean up these warnings now that I know about them. I'm not going to worry about them right now. And use function MLS. There. Maybe I don't need these. Well, I will need this one. This is multi-line string. But I will leave it till we actually have something. The val I haven't touched, so it does have all these issues that I didn't know about because I wasn't running a linter, but now I am running a linter. Okay. These all need to be done, but let's worry about the things that I just changed. What's wrong with these lines? Oh. Oops. I'll change that. That can be simplified to just that. Okay. Typo, sim typo. All right, so those are all, it's happy with all that. And this is ignore white space. Although, yeah, and then this is a separator. The semicolons, pipes. Pipe character is a separator. The semicolon character is a separator. And this is a separator. I think what I'm going to do is when I'm going to pass in the separator as a as the opener for a list, and then I just won't have a closer. And that way you can say, well, like when I do this. Oh, right, because it's in the stash. The thing that I'm looking for is in the stash. I haven't written it yet, quote unquote. The Tenko test, this should also work. And what did I do? I added constructors. And I guess I was going to look for any place else where I use this syntax, t dot. Whoa. I only care about that. Cap, but that's ignore case. I want the case. JDI and JSF. Nil and okay, that's fine. JSF. So JSF needs. This is already a function. Let's do that. Again. Where's JSF? Up here. Oops. Yeah, do it again. But do they have arity? Do dyads have arity? Because I would think a dyad, you would know what the arity is, right? The arity is nothing. Yeah, so PyCharm does all this type inference for you as if it were TypeScript. So yeah, I kept saying I wish I had switched to TypeScript, so I switched to PyCharm, switched my editor instead. Not quite the same, but and then list. Can you compare undefined? I think you say type of X undefined. And okay. And no such X. And then we pass in nothing. What? Right, because print is Python from 100 years ago. Console.log, no such X. No such X, great. And then if we say if X is equal to undefined, no such X. Okay, so you can do if X, so if adder undefined, adder equals that, ATR. And if items is undefined, items is that, correct? And we return this list. Okay. And then so going back to the places where we use this, kind of just want to like hide this representation. So in the eval area, up at the top probably, we say imp.jdy dyad, and it's going to be this. And then this is an int, imp.int, And we're going to return x2 plus y. And then the same thing here, minus, and same thing here for times. And then the same thing here for division, even though what really should happen here, I might as well just fix this right now while it's in front of me. I haven't tested this, but I'm going to say divided by that, but we want to say int math.floor. JavaScript does not have a concept of an integer, but we can do the same thing with floor, do what we want with floor, and then this is a JSF. And the function is going to take x, and it's going to return a string. It's an imp string of imp show, which should probably be something that you import from imp of x. And then the arity is 1. It's imp.jsf. And then echo is the same thing, imp.jsf. And yep, and yes, it returns nil, and then a, and the arity is 1. That's it. Doesn't like that I'm using comma expressions, but I'm going to continue doing that. So, okay. All right, so this is fine, this is fine. In the core, that's probably the thing I'm making. Yeah, this is what I want to avoid, but you have to have it in the constructor, so that's right. And then all these are constructors. Constructor is commented out. And then in eval.mjs, case t list down here at the bottom. Here we're going to say what does list take? Takes a and then the items, right? So we'll say imp list and we just pass in the items that we got from before. So the attributes remain unchanged. And then okay. I'm going to clean up these errors too. I'm just while I'm doing this, I'm do a little cleanup pass. And then imp read close token. This is in the imp reader where we do the there we go. This t just do that while I'm going along. This is going to be imp.list x and that. Presumably this is already imported. Okay. I do kind of prefer the word var, but whatever. What's this mad about? This should be separate commits. But whatever, let's do it. One more line. Move, redundant, escape. I'm changing that line anyway, so. So here, this will eventually become imp.mls x. So all the ones in the core, and then read, and then t top. I'm okay with that. Top might actually become just a plain list as well. It is a list. And it just doesn't have an opener or closer. But I'm not going to touch it right now. I'm not going to create a top. A creator, a function. Let's get rid of top. Even though it's a comment. I'm not going to create that. I think top will go away. All right, so gd imp star.js dash star.js. What? Oh, MJS. So make sure the tests work, and we should get that one about the strand. Yes. So gs git add imp -in.mjs and git commit -m add constructors imp.xxx constructors and minor fields. Okay. Now when we get stash pop, I expected a conflict on eval because I changed that one line down bottom here. Right, so this line right here, what we had before, and we will put this right here. And not use the word return twice. And then here, actually, I think that's the same thing here too. Yeah, same. Because this is like the default handler that was there before. And this is not an invalid imp value, but this is invalid list value, list opener. Should not ever happen because this is one of those things, because we've matched one of these three things. There is no other case. This is old, and this is, so we've resolved the exchange. Git add in eval Sanko test. Okay, well, we modified the test, so that's why that test has changed. But the word projection is not spelled right. This is tedious stuff. That's a problem, you know. You're trying to make these things interesting, but it's a lot of tedious grunt work. Not tedious. It's just like I'm not unhappy with this. It's just, you know, I don't expect it to be interesting to watch unless it's interesting in the same way that, like, you know, people mowing the grass is interesting, and that it's, you know, slightly tinkering with things, cleaning them up, making them nice. I'm happy with this. Am I happy with this? This just plain cannot happen. How about we say we put this here and we get rid of this. Let me just say to do for friends and else. And 2 brackets there. Else return. Yeah, so this is projecting. This is the thing I was building. So we have a symbol and arguments, just like, you know, the head and the tail. So this is the symbol that we're going to look up. So we're going to look up the symbol as a word, and then if this is not, if not f, throw undefined word. So throw project undefined words in. So that way, if we say, you know, like foo, and foo is not defined, it'll say, it'll complain about that. I do see that word as the word project. Hmm. Opener is, okay, I didn't need that part. Sure, why not? And we're going to test add projection so we don't get a bunch of failures. What? Ah, redundant, yes, that's okay. I thought that last eval would call. Last eval calls val list. Why did this happen? Oh, I see. We don't need. So eval list 38 and 190. But why is this happening? That's not JavaScript. Okay. Okay, so now we can see the problem nested somehow. So we've got an eval. And in the REPL, we're not. Oh, it is tracing it. I don't think I get there. Because yeah, it wouldn't. Why it wouldn't be in there? I've done something to break it. Okay, what have I done? This. Right. So what I really want to say is if what's going on here? So the top contains a list. Val list. This was the wrong thing to do. It failed because it says evaluating on it. Back where we started. I'm just going to stick this in a scratch real quick. Scratch text. Whatever, that's fine. And then I'm going to remove this. I just want to separate out the changes I made, the cleanup changes. Oh, that was already there. In that case, so this isn't being triggered. Why not? Not only is it not being triggered, this test is in the wrong place. Like all these tests that we're failing, or that we're passing, are not being tested. So I don't know for sure that I haven't broken anything. There we go. Oh. Okay, yeah, all these tests pass. What is this? Why is this happening? Because this noun is omitted in place. We modify it if it has a thing after it, but we don't do it has an op after it, but we don't evaluate it. If I try and print this now, it's going to break all the tests because the very first test is going to fail. It's not expected output. Can you write to standard error on node write to standard error? Yeah, so you can say process standard out, standard error. Template string. Stringify. I think this is right. I think it actually is. This is like eval is wrong. Hang on. Like I think what happens if I just say no because we do return x. Why? What is wrong with saying x this dot eval x? Why is it wrapped in a? I've got a type error here. Somehow this is. I never get that far. Unreachable code. All right, because of this. But I never get that far anyway. Oh, because eval does not take an argument. But now, in one of the places where I call this, it's only called here. Okay. Oh, okay. Well, then that's fine. When I say enter, it pushes here onto the stack. I think it's okay to say this. Yeah, because this is. Yeah, I don't. That's actually a perfectly fine imp value. Oh, but we say. And everything is fine except for that one. Except that I'm printing something. Is what? Opener is this. Right, so this is now being invoked. Boom, boom, boom. This is being invoked now. And something is printing out the word null. We got back null instead of this. So we need to return this project about this. So project, is it returning something? right. This is the last thing that happens. So this is when you evaluate a list, you get back a list. But last eval, we're saying so arg0 and args1 should give me different answers, right? Arg0 was this, and what is TB? Tree builder. And this is my list of args, right? So my first arg is this, which is fine. That's what's creating the nest. Oh, wait, why is this? Why is this here? This should be the value. I've appended something to it that's okay. I create a list. What's causing that to happen? Man, do I even want to build a language with gradual typing? Do I just gradual typing works great when you're using an array language because you hardly ever have. But even then, like even in J, sometimes I have issues. And it's a needle in a haystack problem. Works fine if you have small things. And every once in a while you run into something like this. What is going on here? Everything is passing until here, so the error has to be in. I mean, that's right. So we have echo 4. Should be in here. We see this. And we're seeing it here, so start from the top. Cool. This is correct. And then arg0 is already this. Arg0, we've already introduced the problem. Ah. This is it. Wait, no. Args is just a plain JavaScript list. That is correct. Args push arg. Ah, it's this. This is the one we need. Imp push arg x. Now this is correct. So I've solved the problem. All right. So the test first the test is documenting something that is not correct. I said this is what it should do. This is what it was doing before, but now it does the right thing, which is what this should do. So this is actually works. We've got projection syntax at least potentially working. Args1 is undefined, undefined, undefined. But why? Okay, why is that? Is that a bug? I don't think it's a bug. Undefined for undefined. It's trying to print out the wrappers for this list. And that is because yeah. It's actually open and close, right? Okay, so that was the problem. Maybe we'll use brackets for this. I don't know what the right thing to think is here. Maybe just leave it blank. Maybe leave it with a space around it. I don't know. Unicode brackets. Maybe just use some other kind of special bracket because I. There we, come on. Can't give me a UTF-8. Like that. Right, and this is only being used internally, so it's going to go away anyway, so it's not a problem. Whatever we want. All right. And now we're back to filling the strand notation. Oh, so this worked. No, this worked fine. This worked fine. What about nested projection? So now we want nested projection. Plus 2, 2. Let's just even kick it up a notch. Undefined word. That's a bug in the parser. All right, let's commit this code and then we'll add that test back. Echo test. Git add imp core imp eval imp tests. Git if of these. Yeah, one of these had a composition thing. Or projection syntax. But anyway, so now we have projection syntax. Projection syntax. I'm just a little bit curious. I just want to make sure my stream is actually running here. Yeah, it says it's live. Okay. Usually somebody comes by, even if they just stay for like a second and then disappear. But Maybe my scary logo scared them off. Or it is Friday night. Go test. Okay, and let's pop this one off. Or whatever. I'm going to change the format of these tests very, very soon. I need to do a little more work on Tanko. Okay, so this is just undefined. Unexpected. Okay, so undefined word. Is that what I had before a minute ago? I thought we had the left bracket was also in there. What did I change? I changed. My bottom line is that a bracket should never be in a word. So that is a bug in the parser, in the reader. And it should not be any of those words, any of those characters. I think that's what's happening. I think that'll fix it. Incorrect. Incorrect. Oh, this needs to be a not white space. This is any word, right? Otherwise, because that's what was preventing it from. So this is right now. So this is what I need. Is that right? That didn't do anything. All right, so hang on, set. So we picked up this. This is right. We picked this up. So now hang on. I wish I had a way to see the tokens. Like I wish I could. I ought to be able to do this as a string, right? And then tokens, something like that. But I wanna see like XML form of this, like some kind of like dump read. Like if I do this, I'm just broke. The whole thing is frozen up. PyCharm is frozen up. There you go. Okay, imp show, and that's not, but okay, I want, wow, it's so slow. So we're gonna import read. What do we have in the reader? In the reader file. That implies a fluent interface that does not exist. Return self, return this. There we go. Make that a multi-line thing. Wait, why does it say, why didn't it? Oh, right, because that's a symbol. It doesn't recognize. Or it does recognize. Oh my god. Because this does nothing. This exists, but it does not. It just did nothing. It returned an empty list, and then it evaluated this, and then it, okay. Because you say this, it'll say it doesn't know what the word is. This is defined. What we actually want to do is import a function named impread. S, so imp string. We're going to send S to I want to give like a type annotation, like imp string imp 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 data, something like that. I have RL wrapping. This isn't going to work because this doesn't do what I wanted, right? So now we have to say import imp, or just say import read from imp read.mj. It's reading the second character out of that. I need a better way to look into this, right? I need like some way to. Right, so this needs to be a separate test all by its own, regardless of this. But this is projecting an op. It doesn't give me a real trace here. That's weird. Why doesn't it give me a trace? Word class. Invalid argument sep. Okay, so right, that should never. So I need to know what the class is. So how about we say class? Imp JSF, right? So it's a JSF. I would say WC word class is an imp JSF, and it's going to be X, and it's going to be word class X. This dot word class. Oh, but we don't have a. Doesn't use this. So we're just gonna say word class return word class X. In fact, we're just gonna move this here, do this here, and then this will be a top level function. There's return up here at the top. That's because it's just a symbol. It's like part of speech. Part of speech. So here we're going to say eval, right? Wait, do I have a self-host? Sorry, part. That's a noun. We say eval. Part. A noun. That's also a noun. It's not looking up the word. So we want to say like lookup. These are just temp words. This is not part of the. I'm just making something up right now. say look at it. So we'll say look imp words x. Imp words x. Can I say that? Hmm. That's kind of cool. All right, so read oh, that was and fix this. It doesn't. It's not doing projection here. Hmm. Yeah, the nice thing about doing these tests up front is that when I do this the right way, you're going to have to build all these little tools up for debugging the thing from the start. Projection op is sending +2 comma 3 or 2 semicolon 3. How do we parse that? We see that we're not even seeing right? It does not see that as this. So it didn't parse it this way. The reader didn't give me this. I wanted to see what this is. This should have parsed this, and we should have a node here. I think I have enough words to debug this, but how do I do it? I have to say, like, I have to make a word called like XML. Actually, we don't need this at all. Imp string to XML. You can do it, yeah. Perfect. Sure. See? Our default, we're going to return T, B, or maybe for all of these, we'll do a fall through thing. Case T dot sep case T dot int. Yeah, like all of these, except for that one. Maybe some of those need a string definitely. This is supposed to be about this. Is supposed to be about debugging, right? I don't know why it does that to me. That's right. Okay. That doesn't seem right. Because I didn't do this. Nope. A, and then the content is this. Right. And same thing for dot list. What that says. Okay, well, that's very helpful. This is what I expect. All right, so we have a list, but it's not being projected. And why isn't it being projected? Let's check this in first. Let's get rid of that word projecting. We printed it out. I'm going to get rid of it in just a minute, but I mean, I'm going to re-add it. Just the AI types this so fast that I don't mind just deleting the imp read debug statements like that. So ga star.njs git add ch scratch.njs. Git restore stage scratch.js. Didn't mean to put you in there. Actually, what is that? Ah, okay. There's a note that I'm coming back in a second. We'll just get that. cd cached. I don't think I actually added any code here. I just added a bunch of to the repo. See that? Okay, so Tanko test. All right, so what I think I learned from that is that if I say this is not being projected, this never gets printed. Oh, it does. Oh, yeah, no, that was from the previous test. And then when we say Tanko test projection op, it does not say this projecting thing. So we didn't trigger it. But why didn't we trigger it? Because This is a list with these openers and closes. So why does it not match this? Console log. This is log x. Maybe M is not working? Oh, it matched. Oh! Don't evaluate the list. Could we do it here? We have to do a special. Okay. But it wasn't even that. It wasn't even the plus at all. It was the semicolon, which I guess I should have realized that. But I thought it was. I thought that I did. Yeah, I didn't use the semicolon before. So the new thing is not that. It's that. There we go. And it worked. And the test passed. Well, the test would pass. Why does that fail? How do you mark something as executable? What is this? Because Windows does not have a concept of. How does git bash for Windows mark things as executable? That doesn't make a lot of sense. I guess it is, but okay. I forgot what I was doing. I want to get the XML of this. Right. But it sees that. And then inside of it, it sees a list, but it doesn't. Okay. I would think that would call the projection syntax. Oh, wait, is the test wrong again? I'm dumb. Hey, Batlin. Care about user bin node. I don't know. My question is, how is this working? How Windows does not have a concept of executable attributes. So is Bash doing something magic or the ls command somehow inspecting the Git repository? Like did Git Bash ship with a special version of ls that does something, or I don't know. I think it's using some kind of like it's showing this as having an X attribute, but that, as far as I know, the Windows file system has no such thing. It says no one's connected. And it says I'm not connected. So I don't know what's going on here. But thank you. Doesn't matter. Okay, so that nested was completely because of the test. What I need to do, Tanko needs to show the test input, and like that, like the expected output doesn't matter because you get the diff, but the test input needs to be shown, and I can do that by going over here to Beaver Tanko. I don't want to open up another PyCharm window because So slow. It's under Tenko, and then that would be in the, like, switching gears to another project. Not on the top of my head right now. It's in the reader. It's in the, okay, what am I trying to do? I'm trying to print out the test input, and that should be in the runner.py. Apparently it was already in memory here. And then wherever it says how to patch, nope, test it's this all this stuff right here is not reachable anymore. Shoot. We don't have the actual test at that point. That's why it doesn't do it. I'm breaking things left and right here. Test name. Oh, but this actually doesn't require that. From a thread in Reddit, it seems like the executable mode thing in Windows Git Bash might only be relevant to Git repos. Yeah. Yeah, not the file system and the shell knows. Yeah, I think that makes sense. That's what I'm getting, because like they probably patched ls to do something. So this can be test.name. I'm trying to get the test to show me what the input is here, because I always have to keep looking here. I'm a little bit off topic at the moment. Test. I don't think this is reachable. This should be test. So that should be m.test description or none. Oh, just t. We'll call it t.name. How about we just say tn equals t.name? Goes back to t. .name is fine. This is the only place where it needs to be. I think that's going to work now. Ah, of course not. Test is not defined on line 272. It's true because I called it test instead of T instead of that. Done? Yes. Okay, so now we can see what this is. So I didn't have a description, but input given is echo hello, and it's projecting echo. And the reason it fails is because it has this debug line in it. Okay. Test trans failed. Input given. Why is this number here? This number thing. Head print. And this is like a headline kind of thing. And then if t.body print print this let's leave it like that. Okay, test trans failed, input given 1, 2, 3, 4. How do you patch your output to pass the test? That's fine. That's where I was failing before. I don't have it set up to do the whole thing Tenko is supposed to do is to like allow you to add and remove tests, and so you can have tests in the future that you're queued up, in the form of a challenge or whatever to work through. But now that I'm using it out of a file, it's not. I'm using it out of this org file here, which is where this thing. All right, so I'm going to leave all that for next time I work on Tenko, which is going to be very soon because it's not working for people, and you can't load multiple. You can no longer do 2 attempts at the same time. So no good. All right. All right. So back to this. So I've completely lost track of my context. Oh, everything's good. So what did I change? Basically, I did a bunch. I had this line here, and that was causing a test to fail. And then I did like so much stuff to debug it when I could have just said that line does not belong. Okay. Well, I guess I wasn't doing it. I was annoyed that the input was. Okay. So it does need to be removed from input val. Wait, what? And project. That was not the actual problem. Oh yeah, it was. Right. I'd added that then. All right, so imp yes. Okay, that was the fix. And what was the change in gd imp test.org? Just more projection tests. Okay, so git add imp mjs and imp test.org, and we will commit. And what are we committing? We're committing that we got the test, whatever the input val thing is. Fixed projection. So basically, because it was breaking on the separator, right? So fixed projection for multiple arguments. Fixed projection for nested and multi-arg. Okay. Okay, so the whole point of that was to get this projection syntax working. And then, and I wasted a lot of time. This is what, 3 hours now. This was meant to be, well, I didn't know how long it was going to take. Right, but now that I have this working, I want this to be the only thing that the JavaScript interpreter knows how to do. Because I want to make the JavaScript interpreter as simple as possible. And then we're going to lift all the logic of parsing after, I'm calling this thing a token tree. So or minimal syntax, MINO, minimal notation, sorry. So, or Mino, I guess, as in tetramino. So you parse the balanced thing into a token tree. So this is the start token and this is an end token, and then it's got a list of stuff in between, so which we can now do with the XML. And then the idea is that we will use this syntax to bootstrap parser. I'm gonna run to the restroom for like 1 second. I'll be right back. Okay. Wait for I get a better face tracker on here. I know it's always like the camera's moving back and forth, but it's not. I'm moving back and forth, and it tries to put me in the frame, and then it just doesn't always do a good job. Garbage. Like I imagine most of this stuff is garbage. Okay. It's old school. I just delete all this stuff. Don't know what it is, don't care. Why is that different? What have I changed? Oh, okay, flip the to-dos. Yeah, I'm not gonna. That is okay. I'm gonna make just a document what I did with this. So we said XML 1, 2, 3. 1, 2, 3, 4. So this should be a test. I want that to be to work. I don't know what imp is yet, but I don't have an imp mode for Emacs. But so echo XML 1, 2, 3. Maybe we'll do 3 and 4. Well, this will pass because and we need to give it a name, which is again redundant. This will change in the future. A better syntax for these tests. In fact, I'm probably going to use implish. I'm probably going to use this notation to write a new syntax for these tests, rather than just using an org file, or maybe org embedded. I don't know, something like that, like an org dialect of. But name is what? XML. 2XML or something like that. Maybe I should call this 2XML. How about XMLS for XML string? This is only a debugging thing, and I'm probably gonna have like a better name than. And in fact, well, what I'm thinking is that, like, you know, this minimal notation is going to have like all kinds of different containers. Like, it's just symbols inside of containers, space separated symbols inside of containers. But it's going to allow XML as a syntax. So this ought to be parsable. And this should say sim. This is actually wrong. V equals 4. And then all of these, I think, just replace. Oops. Whoops. Just hit the wrong keys and then my hands are too big. The string. All right, so we're going to do that. And that way the bare tag will be fine. Okay, so we're going to call this XML string. Where would that be? That would be in the interpreter eval. And we're going to just call this XMLS. Yes. So, okay, the question is, I don't know if you, yeah, I think this preserves, but is this just testing the parser? What's the meaning of the semicolon separator in the list? Is it like, hey, making one to a stranded sublist? Yes, that is exactly it. So I'm thinking of this as a two-dimensional syntax. So yeah, you know, whenever you parse something, the computer sees it as just rows of characters, but you and I see it as or it sees it as one row of characters, one long strand of characters, but we see it as like a two-dimensional thing. So I picture these containers as a two-dimensional object. So when you say something here and then you use lines, rather than just having this be like a single, like a vector, it's actually going to be a list of vectors. So 1, 2, 3, 4, 5, 6. These will be separate. This is a list of, I don't know, maybe I don't like that there's it's as if there's one here and here, like a new line, like a separator here and here. So you have 3 items in this list, which I really don't like. So maybe I'll change it slightly and do it like this and just ignore the new line right there. I don't know. Or maybe I don't really know. But maybe I do something. But the point is that, yes, the separators, this is a separator, this is a separator, and a new line is a separator. Or maybe new line is not a separator. Maybe I don't do that for, I don't know. Maybe I need to have some like smart rules for whether the new line becomes a separator or not. Anyway, but these 2 characters at least are going to be separators. So the syntax is 1, 2, 3, 4, 5. This is the test that's failing right now. Right. Well, all the tests are failing right now. No. But stranding. Strands. So this test is that if I give this, I should get this back as one single token. Right now it is not one single token, it's this token. But I don't think this should be a... This is part of what's causing me to split the idea of the parser into 2 steps. So we have the reader, which just reads nested tokens and then sees these as 4 separate tokens. And then once we have these tokens like floating around inside of lists, then the actual language parser is going to, like, the real thing is going to come by and parse that into the K style. K doesn't care about the length of the array. No. So it's called a ragged array. So in J, if you make I don't have J handy. In J, actually I probably have it right here, don't I? I'm firing it up already, but yeah, there's already this one too. I should probably leave this up in the terminal because I always close the window here. But if you say 3, 3 reshape of I9 or whatever, you get a rectangle. It's always a rectangle. You can't make it not a rectangle unless you do each line like that, which is very small. And now you can make these whatever shape you want. So you can say 1, 2, 3, 4, 5, and everything's good. And you can have different shapes. So a K, in K, you would say the same thing. And you would get the structure back, but like it doesn't print these boxes because just everything is like this in K. Everything is boxed. Yeah, boxes get around that in J. Whereas in K, actually K doesn't even have 2-dimensional vectors or 2-dimensional arrays. It just has vectors. So if you have a 2-dimensional vector, then it's just a list of vectors. Like a rank 2 array is just a list of vectors. That's right. So the vectors can be any length you want, because you never make a rectangle. You only make lines. And I don't know about that. I haven't decided what I'm going to do there. I'm probably leaning towards the K style, but maybe I don't know. Maybe have a special type for like maybe recognize that it's a rectangular array. Also, the other thing that it does for J is it allows you to mix the types, whereas K has a list type. Whereas here you can say banana. Oops, no, you can't say that because that's not K. That's not J. You can say that in K. You cannot say it in. Oh, leading axis. I explained this to someone last night. I gave an example of someone this last. Not in here, but in the APO farm. Do I find it in the J channel on here? I have an example right off the top of my head. Leading axis theory has to do with how things are. Oh, I can't make this bigger, can I? But the idea is that, so this is, if you can't see it, it says 2, 3 row I, a row iota of 6. So it's 2, 3 reshape of count to 6. It goes 1, 2, 3, 4, 5, 6, and then you add those together. So take that same expression, add it together with a plus slash, whatever, and it's called plus insert in J. I don't know what it's called in APL. You get 615, whereas in J, you get the same. You have to add 1 to it to get the, and also use different symbols. But when you do that, you get the rows added together versus the sum of each row. So there's different ways to do it, and then Rawl pointed out that you can do different things to make that happen. Yeah. So I don't know what the leading axis is, but I guess one of these they have different leading axes, I guess. So it's whether you think about. I couldn't put it into words. I didn't follow the debate on the arraycast, and like I get what they're saying, but I don't know what I'm not. It's not a reduce. It's not sum reduce. It's I mean, it is. It does the same thing. No, it's not a depth. Hang on a second. Right. So plus, this is called insert. And so what it does in J, I don't know what it does in APL. I don't know what the semantics are in APL. But in J, what it does, what the slash does, is if you say 1, 2, 3, 1, 2, 4, whatever, it's the same as taking that plus sign and inserting it between each item of the array. 2 plus 4, right? And so if you have this, right, and you put plus, then it's the same as 1, 2, 3 plus 4, 5, 6. And so that's why you get 5, 7, 9. So it obviously does something different in APL, and I don't know what that is. Yeah, there's a lot of theory. People talk about theory and this stuff. I don't follow the, like I like the arraycast. I was on it one time, so that was awesome. And I am a fan of it, but I sometimes it's a little more in depth. You know, they really like to get into the theory of these things, and to me, I just kind of like, you know, if it doesn't do what I expect it to do, I jiggle fiddle with it until it becomes until it works, and then I get a feel for how it works, and I don't always have I'm not articulate enough to explain the rules. But in this one, I can at least explain why. So yeah, I don't know. To me, the languages are pretty much all the same, and then there's some weird cases, and you just get used to them. But I don't care so much about the theory. I like to just build software, and you know, if I like nice notations for it. Anyway, that's that. So your question was why that would, or whether that had to do with. The answer was no. It has nothing to do with reduction, but anyway, yeah. In this language, 1, 2, 3, 4 is going. So again, I'm making like a series of languages, right? So implish. Yeah. Well, it's funny because I wrote a Twitter to Connor Hoekstra one time, and I said I pinged him on Twitter and I said something about like I tried to explain a concept that I was using like getters and setters. I made these verbs that are getters and setters and tried to put them in a fork. Like it's just you can't. I made this like long thread and I pinged him in it and I was like, he said I don't really follow that. And it's like, well, yeah, because I didn't give examples and make it. And it's like, oh, I got to make this into a video. And so now I just don't try to explain it to people until I just put it in a script or whatever. Anyway, I'm rambling now. Yeah, I'm not good at explaining things on the spot. When I sit down and think about how to explain it, like right now, I'm taking like months to prepare like a lesson. Right, like to me, I think of like this timeline in my head of like walking people through something and what they need to know and all that stuff. And it's like I see like prerequisite trees and sometimes you can draw them. Right, like here's my tech tree. Right, so if you have this virtual machine and then you right, like the whole goal of like my lessons and come on, you have to walk down this path. You don't understand. Well, you can understand JSON, but you don't understand the JSON parser until you understand the things underneath it and like how we got to this point. So now once you know this stuff, once you know the virtual machine and the assembler, then you'll be able to it'll make sense to say, okay, I want to implement consoles or an allocator on this, and then from there I can make tree structures, and then from there I can make implish. And so I think about that and like try to like walk people through it, and that's how I plan things. When I do it on the spot, it's just I'm all over. Like that map is in my head, and I'm just trying to explain everything at once, and it just doesn't work. It's a serious. I think I call it the Gestalt problem, right? And I think everybody suffers from this. I'm just acutely aware of it. But like when you're trying to read somebody else's code, you know, you're seeing a graph like that, but it's already been serialized into a tree, and the tree is not the way that you would want to learn it, right? The tree is not organized in the way for learning. It's organized, based on things that are similar go into this module, and things that are like this go into this module, and this piece is over here. But when you actually build the thing, what you want to see is a tiny version of the system where all the pieces are working together, and then you build it up from that. So you don't want to see it in pieces. You don't want to do an autopsy on the thing. You want to see it growing, right? And it's much easier to start with, oh, there's a little tiny thing, and it's I get to know how it works, and then it gets bigger and bigger, and you see it grow over time. So that's why the tests are in a particular order, and you start from a very simple system and you work your way up. That's why I start from just a virtual machine that's just a stack machine. It's like, okay, and then you add this and you add this and you add this, and eventually you get this weird language. That's another reason why I'm saying, well, it doesn't make sense to make the parser so complicated right now when I can just make, when we can just have a language that is just this projection syntax. And then once we have that working and is all working and everything's good, then we say, okay, now let's use that to define some grammar rules or grammar combinators and things like that. And then we put them all together, and that's what I'm thinking anyway. Anyway, that's it. Yeah, I'll stop rambling. Anyway, so what do I want to do here? I don't know. I don't need that information anymore. It's really hot in here too. Oh, I think there's a heater underneath this. Yeah, it's true. Oops. Oh, but this test is not working. So Panko test. The XML test is not working because I changed the spec. And the symbols are not working. So let's do. I think XML is up at the top here. This probably ought to be moved to its own thing. So let's say, oh, right. XML tag. Sim, and it's going to be v is no content. So that should fix that. When you read a textbook, the optimal order of section is unlikely to be the actual chapter order. Yes. Yes. Because it's hard to go in depth into something, you know, without, I mean, you want to focus on it, right? And you want to study each thing in isolation. It's analysis, right? Like people, you analyze things by taking it apart and looking at each piece. And to some extent, that's a good way to build software. But you do it iteratively in software. You do it, you know, like it makes sense to, like I was just thinking these XML routines probably should be in their own file. But I'm doing that in the context of adding a feature. And so every time you add a feature, you're going to touch a lot of those little modules. And so you know, it's a graph. Yeah. It's a graph serialization thing. So that's my thought on it. And obviously, you know, it'd be ideal if you know, if you could interview each student and say, well, okay, what do you, first of all, if it were linear, you could say, well, what, you know, how much do you know? If you could get some order, you know, idea of what they know and don't know, you could at least sort those modules into all the stuff they know is over here. Now we focus on the stuff you don't know, but you have to interview them to do that. So I don't know. I figure just leave a trail. At least if you leave a trail, it might not be the optimal order, but you can skip, you know, you can just do the things that you understand how to do quickly. And then if it's broken into small pieces, then when you get to something you don't understand, then at least it's a small problem to work on. That I think you can guarantee for the as a mentor, educator, whatever. You can guarantee that you're presenting somebody with small problems. Optimal order is not something you can guarantee because it is. I think you're right. It's per person. What's wrong with this? Imp. Oh, because the word imp is not in front of it. So that's why I need this to say XML tag, and for each one of these XML tag, I'm going to put the word imp here. But in the future, when I actually get tags, then you'll be able to say put your own tags in there, and then they won't have the imp prefix. And then imp list is okay, right? Because I didn't. Actually, you know what? Let's just put it here. And then T to lowercase. Right, and then here when I get it working, that'll just be a list if you put the opening tag and end tag. Like this is already basically XML, type a tag, attribute, and a v value. So in this world, XML will just be a list and tag, unless it's self-closing. What is wrong here? The test wants something that I'm okay. Hang on. This is a little hard to read. So remove this and add this. I did that. Did I not? No. I did. Yes, tag. Oh, but I didn't put it here. And this needs to be that's probably wrong in the test. I did a search and replace. That's why practical learning is really good. It automatically forces you to explore the most important concepts and when you need them, rather than reading 30 pages of API. Yes, I agree. You got to learn by doing. I mean, like I think when you're learning, Jonathan Blow gave a talk, or I saw it on YouTube. I don't know if it was a recent talk, but I saw it recently. He was talking about the idea of, it was just a snippet of him, and he was saying, like, he was pointing out shallow knowledge versus deep knowledge. Like almost all tutorials are kind of like shallow knowledge. Like even like what we were talking about, the array cast earlier. Like like there's definitely a value in create like an ergonomic value in creating a language that like does things the best way, but like whatever the best way is, but gathering a lot of features that really work well together. But at the end of the day, I don't really like I don't have a preference between APL and J. I mean, I prefer the ASCII syntax for the most part. But if you gave me a good keyboard, when I go to try APL, it works just fine. I just I don't really have a preference between any of those languages. I would happily work in any of them. BQN, WeWa, any of those things. Java, COBOL. I just don't have a preference. Because to me, the important part is building programs. I would be a lot more comfortable in a nice language. Like the nicer the language, the more comfortable I'd be. But like, I don't know. It's not about learning the language. It's about learning programming, and programming is independent of the language. The language is just a tool. So I consider that like surface knowledge, and I'm just rambling again. I know I'm like three topics deep. What is this? It's just nonsense garbage in the test. Oh, because I was responding to your that. I just. There's a picture of my little girls here. I'm going to turn off. I want to broadcast them to the world. Except it's not working, so I can't do it. Probably got some confirmed dialogue. And I don't think it's even showing on screen anyway. I'm rambling. Okay, it's okay. I don't mind that. I'm happy to have people hang out. Like, nobody watches these things. I can't watch them. So it's like, it's just talking is. I'm happy to have anyone interested in the project and what I'm doing, because it's very difficult to get attention, and it can be demotivating sometimes. Well, not really, not for me, but I mean, I just it'd be nice to have more interaction. What am I doing? I was testing. Oh, so this test passed. Yes. Okay, so then we check back this in gd imp eval.mjs test add XML add test and clarify XML's word function verb. Okay. Really, this is just for debugging. But okay, so I also just in the process of trying to debug whatever I was working on earlier, I added like a bunch of words that were just parts of this interpreter that were pretty much ready to go. I just added them as words and exposed them to the interpreter. And now I guess now what I want to do is I want to get rid of all the complex junk I made earlier and just have this nested syntax here. So if we say, well, okay, I guess I want to make sure that the JavaScript parser, the reader here in JavaScript reads everything, takes a string, completely parses it into the base notation, so minnow, which is just token trees, XML tags, curly braces, K projection syntax, parentheses, all those things, but it's just symbols inside of containers. I guess with the one exception of XML tags have attributes inside them. Everything else is just symbols and containers. And then the parser does not yet actually handle XML, but that's fine. And then we're going to have a simple dialect, a simple like preliminary language, like a bootstrap dialect of implish that only follows Hayes projection syntax. And it does two things. So it does, so before we do that, well, right, because in this part is going to be handled by the interpreter that I want to write now, or the parser, the secondary parser that parses this structure, walks this structure, and builds a new thing. And so to do that, I need to implement the match routines. But they're going to operate on tokens. I have a list of them that I always use. So the J implementation is tangent code Cinder, syntax directed extra. So Cinder, yeah, that's right. We needed the tree builder, which that exists. I think what I'm going to do is I'm going to expose some words to the system that allow building the tree, but also, okay, so this is not the right file. This is like the thing that, hang on a second. Tracks. So this is a literal, choose, group, trim, I don't know what this one is. Literal, choose, group. Oh, I see. I'm right. So yeah, this is this is what I need to write today, and this needs better documentation. What this is? Okay, so nobody knows what I'm talking about, really. All right, so it's a parser combinators for J. So, and then if we read this paper, which didn't link directly, but his PhD thesis. Chapter to say? Chapter 2. Oh, come back here. What we get? Oh, can we click on 2? Oh, page 9. These numbers are not the same. Blah, 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 blah. Peg parsing, okay. So somewhere in here, he has like all the rules for So here's the syntax of the language. It's just a parser language, like a description of a grammar, and then he's got like rules for in like turnstile notation somewhere. And then I'm just translating them. Blah, 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 blah. Come on. Yeah, here, that's it. No. You got like a pay, this. Or just this stuff. So basically you got sequences, and so anyway, I gave names to all these things. And I have my own little write-up of this that I thought put in my own words. So that would be tangent storm.github.io. Yes. /drafts /wedgel /bootstrap.org. There's probably no links to this page anywhere on the internet. .html. Okay. GitHub.com tangent storm. Is it draft? Where would it be now? Tangent storm. No. Yeah. GitHub.com tangent storm. D4. Does that still exist? Yes. And then I've moved everything. I had so much junk in here, and it was so disorganized. Draft. How to escape from Pascal. That's part of this course, which I think is the same kind of thing. I don't think there's anything in it yet. It's just how to, that's why there's a retro Pascal. Parsing B4. What's that? Syntax for how to do this and forth. But no, I'm looking for wedgelboot. Well, that's why. wedgelboot.py.org. Okay. Oh, and I left a trail. Look at that. Our goal is to bootstrap an interpreter for a new programming language. We would like to build it incrementally from the ground up. Wedgel is like the higher level version of implish, where I put all the garbage, or we'll put all the garbage. I did this. I've been thinking about this for a long time. Rather than writing a parser by hand, we would like to model the language syntax and semantics as data and pass this data to a generic grammar interpreter. Yes, that's what I want to do. We will build the grammar interpreter incrementally with test cases. Yes. For starters, we will focus on simpler regular expressions, much like Python's built-in RE module. You see, this is going to be like the good part, and it's like 4 hours into the video. Okay. That's why editing is good. All right, matcher. Obviously, the concise syntax provided by the RE module is nicer than building pattern structures by hand. We will address this soon by bootstrapping our own parser for grammar definitions. In the meantime, we will build our rule definitions by building data structures with Python's names. Okay, in this case, we'll build it with Wedgel. All right, so from these are accessors. And then these are the things that we're going to build. So basically we're going to build data structures. Oh, how does that work then? Well, code is data. So we have to build, so I have to build a each one of these as a function, and then we're just going to write the interpreter Right, because it's homoiconic, so I don't have to have a data structure to represent the grammar. The grammar interpreter is just the interpreter. The Wedgel interpreter will do this for me, which is the same way I did it in J. Although J is not homoiconic, but you can compose functions very easily, and so I just did that. Okay, so I need to implement these functions right here. So emp always matches. Do I need a grammar interpreter, or can I just use like this is just a like I can just use the AST, right? I can just use the. Give me a second here. I need. Well, let's see what we did here. We're gonna build these functions. You know, so you build a structure that says what your grammar is, and then you walk that structure, and basically each one of them gets translated into a function call from parse state to parse state. So they take a parse state and they give you back a new parse state, which means you have global variables, but that's fine because global variables in implish are really that's what an object is. You just have variables that you've defined in your program, in your state. I know I'm rambling. I don't think this makes any sense. Let's read this. Okay, so generic dispatch, since this will be composing instances of these types into trees and wants our system to handle the interpreter. To interpret the types differently, we need a way to map each to an appropriate handler. We will implement this using a basic class. Simply maps each name tuple type to a method with the same name and a given prefix. Okay, and yeah, that's obvious. That's an interpreter. Okay. So we need to keep track of where we are in the input sequence. The following helper class will do the work for us. So this is our cursor walking through the text that we can move back and forth. Matching should either produce a match object which stores the match text and its position within the input, right? Or a special constant called fail. So fail or match, okay? And when I implemented this in J, I did it as just there was a bit in the parse state. In fact, I'll look at that in a minute. A name tuple to represent the match state at any given time. This state includes the match result, a cursor marking the position in the string and in the environment, which we will use later on for storing state. Now we can start building the matcher. First, we will set up the dispatch stuff. Like in my mind, I want this to be like really super simple, but it's not. Like I want to start with the idea like this character matches that character, or this symbol matches that symbol, or this data item in implish or minnow or whatever this is matches this other data item. Like equal. But we do need like a cursor, right? And now this is nested too, so. This isn't, we're not just parsing a string, we're parsing a nested thing. Already nested. Which I guess is not a big deal. But we'll probably need an extra. Actually, this guy does it. He does tree transformations in here. whereas all these are only parsing strings and turning them into. All right, so you have to have the matcher, and then once you build a matcher, then you match. Whereas in implish, how is this going to work? This is going to be something slightly different. We're going to probably have like, let's do these tests. Let's work our way up to this test. So empty match should match hello. That's easy enough. Right. So future stuff. All good. Ignore these failing tests. How will it know when an expression is finished? I probably missed some really obvious context in previous streams. No, I haven't talked about parsing at all. But it doesn't matter whether it's finished. So what happens is a grammar. If you want, I don't know if you've ever done any parsing, but for anyone who's watching this who's never done any parsing, search for ohm.js. Actually, I think this was even on Hacker News earlier today. But that's not where I first discovered it. But you go to the editor here, and you want to parse a language. Do I even have mine? Oh, I do. Okay, so this is Minnow. This is Minnow, and it saves it in your local storage, so you can do things. So, or this is an early incantation of that. So you say what your grammar is, and this is very much like what I'm building right now. This is ohm was made by a team, including the person who wrote that paper that I'm looking at here. So ohm is like Ometa 3 or whatever. It's now a JavaScript thing, and it just does parsing, and then you get a walker for that tree, and then you do things. So yeah, right. So the question is, can you translate Bacchus-Naur kind of specs into that form? Yes. So BNF is a very, very simple syntax for grammars, a specification for grammars. And then there are various extended BNFs. Hang on a second. Sweetie, what's up? Come in. Be quiet, okay? My little girl's here. The other reason I do this is with people watching. Is that it helps me imagine. If I know people are watching, I won't sit there and say the same thing over and over again. But it's also good to have questions. But this is all kind of like a rehearsal for like videos I really want to make on my main channel, which I haven't done in like years, 2 years almost, I think. But coming soon. All right, rambling. Anyway, each of these things so are replaced with a symbol. So we have definitions. So in my world, let's rewrite it in my syntax. Well, maybe I should make it first. So for example, why is this not? There we go. So we can paste in this. And it looks like it parses. So why does it parse? Did it parse? let's see. So it says it parsed, and we can look at each step here. So it used the text rule, and then drilled down here so that we had word. So item and a word. So that did match as a word. Oh yeah. So yes, I said anything that's not a thing, but it did not parse the way I expected it to parse, because, or the current thing parses, because right now it says we have blocks, parens, braces, strings, nums, or words, but we'll call this like named. And then, so you have to declare a rule called named, and that's going to be a word. I think you have to do some, not a space, and then this. And so, did that work? And then item star, and then that. And so now what do we have? Now we have named. That's right. That is correct. So it parses that, parses that, parses that, parses that. Yeah. They did a really good job visualizing that. It's really nice. And the syntax here is, I think is, I'm probably going to do a little bit slightly different syntax, but you know, there's a bunch of these things. This is just one of the nicest, and it's like you can go to the web and set it up. There's another one called Antler. You have to download it, and it's got like books written about it. And Antler is really nice. ANTLR. And they use slightly different algorithms and whatnot, but yeah, this one is really nice. So anyway, I want to implement something like this. And you know, when I do these 900 hours of rambling are going to boil down to like, you know, a 20-minute video on how to write a parser, and I'll say, well, go here, but if you know, let's also walk through how to do it yourself. So basically, though, the point is that this is going to work no matter, because it starts at the top, because it says what echo is. So the default rule is what? How does it know what the default rule is? I guess just whatever the first rule is by default the default rule. And so it says, well, there's a bunch of items in here, and then item is either a block, or in fact, you can say explain parse. And you can say, well, what is this? Well, it's a text, and then that's a bunch of items. So item star is there's a bunch of items in here, okay? And so then that means the first thing must be an item, or should be an item, right? And so an item is one of these things. And well, okay, we just try each one in particular, so, or in order. So block failed. That didn't work because it didn't encounter this token right here. It's looking at an E. All right, well, paren failed because it didn't encounter a paren. Brace failed because it didn't encounter a brace. Named, well, it sees a word, okay. And then, so then there's the word. And the word matched. So just any plus that isn't one of those things. Isn't a space in any one of those things. Then it found a space. Did it find a space? No, it did not find a space, which is fine because these are right, because it says do not match a space. So then that matches the thing. So you can have ambiguity with multiple rules, and it'll try out. So this is a peg. This particular thing is a peg parser. What you're saying, if you have ambiguous rules, it depends on your parsing system. Antler will say, hey, you've got ambiguous rules, and complain about it. This is called a peg, a parsing expression grammar. And the idea behind that is that these are just checked in order, and whichever one matches first, that's the one that succeeds. But like for example, like there's some ambiguity between the word, you know, so this starts with word, and then word is an option over here. but it says, well, word, and then if it's immediately followed by this, then that's different from just a word, right? So if I put a space here, we'll get a completely different parse tree if I can edit it again, right? So I put the space right here, because then this token is going to change and it won't be a named anymore. Yeah, so it's no longer named. So we have a word and then this, and so it is named, huh? That doesn't seem right. Maybe this didn't trigger the word packet. This is a me not knowing how to use this tool properly, because I don't know how to not allow a white space in here. Oh, I know what I could do. I could just say bracket. I could just say this opener. So say open. And now if it's lowercase, then that should be a word, and then we'll just do it like that. So if we say open item and then remove this, now it's a token, so this should not match. Oh, I didn't mean to save that. So this is now named, the plus is named, but the item is not named. I think maybe I was fooling myself in that. But now I think if you put a space in between this, then this word named is going to go away. Yeah, so it went away. Anyway, that's it. Me rambling. And it so does it backtrack? Yes. Where the alternatives are, it does backtrack. And so the way Ometa did it, and I don't know if Ohm does the same thing, but basically if this said like ABC and this said ABC, like ABCD, and this one said ABCQ, you have to parse ABC on each one of these things. And I believe this algorithm just it can recognize it doesn't compare the two rules and say, oh, you both have the same prefix. What it does is it says, I remember parsing ABC, and it just caches things. And so when it gets used again, it's called a pack rat parser. In fact, the article that got linked on Hacker News, I think, is called "Visualizing a Pack rat Parser," and it's by one of the authors of this tool, and it just happened to be up there like today or yesterday. Yeah, but if you have a I don't think I need a complicated parser for this. Like, I don't think you need these for certain reasons. Like, it can be very wasteful if you have to look ahead super much, and it's ambiguous and things are ambiguous. But I don't expect to make my grammar ambiguous. Because the things that the part that is ambiguous is like how many arguments a thing has, and that can only be done at runtime anyway. And so the parser has to be done with a knowledge of what the word, just like in J. Like if you say ABC, A space, B space, C space, that can mean anything. All all the parser knows, if you had a J parser, would be this is a train of 3 tokens, A, B, and C. And depending on whether A, B, and C are nouns and verbs or conjunctions or adverbs, then it means completely different things, depending on how they're defined. And likewise, in implish, this is going to be the same kind of thing. You just have a tree of tokens, and depending on what those tokens are defined as, they do different things. Although there'll be some, if you put the word JSON in front of something, then all the tokens should match what a JSON thing should do or whatever. And so it should be able to parse JSON. first with the reader, get a bunch of tokens, including things like semicolons and colons and curly braces and stuff, and then second, turn it into a dictionary and whatnot into passes. So this is actually pretty easy to write by hand. In fact, most of my, like the reader that I have now in the reader imp-read.js is basically doing what you see here. I call all of these things lists, but like I just hand wrote the thing. And then you get, and this is ugly, very, very ugly. But I would much prefer to use something like this, but I don't, I'm not going to implement. I say it's fine to do it for a very small syntax like this. Just implement it however you need to, especially if you're building it up one step at a time. And then if you're going to do something serious, then you should write a explicit grammar. And I want to make, use this syntax right here that I'm writing to write a grammar. So let's write this grammar. So let's write this grammar. So so we'll say like gram, and data is going to have curly braces. So so we'll call it Mino, or maybe we would say like Mino is equal to gram. Regex look aheads can be expensive for sure. Yeah, but so this is called a LL1, or what I'm envisioning this being an LL1 grammar. Look ahead, look ahead one grammar. So you only have to look one token ahead. Except this subsyntax is going to be, it's going to have suffixes like this because I like this syntax. So in other words, to parse the grammar is going to require, well, it still might only be one token because all the look ahead tokens are like one thing. There's nothing you can put after this that changes the meaning of this, right? You could put a long thing here and then put a pipe after it, and then, but no, that doesn't require look ahead because when you parse, okay, so the grammar for the grammar rules would be something like, rule is equal to like alt. Let's see. Well, it would be like, it'd be sequence, and then the pipe character, and a sequence, and then any number of those. So actually, it would be like an ID. So it's a word name, and you probably want something to say like name story, or I don't know, maybe it's name or. And then the word, and then the seq would be a rule, right? So, so you'd have a word here that like name would be a word, something like that. I'm trying to make up the grammar for the parser. Well, what does this do? I think what this thing does is it just makes a function for each one of these things. And so you say like on text, you do this, and it gives you like what the name of what thing matched. So it's either, so like on item, it's going to say block or parent. You're going to get a string that says one of these things, and then you're going to get the actual value, and the actual value will be whatever complicated tree structure you got from parsing that thing. So it doesn't actually use the word name. What you do instead is you say on, or function. You write a JavaScript function on rule or something. Or actually, I think it's you have a dictionary of things, and like semantics is going to be something like I don't know, you can just read the docs on this thing, but it's going to be something like item, and then the item has a string associated with it, like item, and then you would say like node, right? But I think you can even tell it to like say like item block or whatever. You can give it different. They've got it really nice like this. So basically, you write some kind of function that knows what that tells it which one of these you want to accept, and then you get that, or you put the suffix on there that specifically, or either you get all. I don't know. Let's look at the docs. I don't know if this matters or not. Like, I'm just kind of like, I'm not using. This is like shallow knowledge again. This is like knowledge about this particular tool. It has nothing to do with parsing in particular. But this is a very nice tool, so it's kind of arithmetic with semantics here. So you put the grammar into a string, and then you write your semantics, create semantics, add operation eval, and then then you just make functions. This is a dictionary containing functions. And so the word exp maps to this function. It takes one argument e, and you get that node, and you just evaluate. Okay. And so an expression just has the add expression inside of it. The add expression has an eval because you've added the semantics thing, and then maybe make this bigger. Yeah, so here's an example where they've made a rule that matches the left side, and then here they've added these little comments that give you a name for each alternative. So this alternative is called plus, and so you can match it with add xb plus, add expression plus. Plus, minus, or pry expression. And I guess this one is unnamed, so it just goes to that. So if it didn't get matched by one of these, then it goes to this one. This is actually really nice. So then you can just write a handler for these, and you don't have to give these names because you can name them as arguments. And so it's like matching the, and then there's actually a rule that says, if you don't add one of these names, then they have to have the same number of arguments, which is why like you couldn't just like stick this definition in up here because this has 3 arguments, whereas each of these is only 1 token. So you can use the comments to make bin op expression actual bin op name. Yes. Yes. You say bin op add expression underscore minus, or bin op expression or whatever. Yeah. And you can give it a name like that. And that, so this plus is triggering this little suffix here. And then you see it's got 3, 1, 2, 3. And so you see it done 2, 3. And the op is just every token is given to you. And these libraries also like get rid of spaces for you. So yeah. So this is new. This was not in the paper. This is they came up with this after. His name's Alex Worth, or Alessandro Worth, Warth, and I think this guy is involved in it too. There's several people. They were fun. They worked for Alan Kay on Viewpoints Research Institute, where they were doing a lot of the same kind of like build a tiny language and tell the world about it, and they spent many years on it. A lot of good stuff came out of that, but you know, they ran out of funding, and then Y Combinator picked them up for a while, and they were funding this for a while, and then some of these projects. I think they ran out of funding there too. But yeah, so all right. Well, that's enough about this. Question is, how do you build a thing like this? Because I want this concept to be like a core part of implish, right? Like I want to steal this idea of having. Well, Ometa was like a programming language with this stuff inside of it, and Rebel Rebel and Red language also have a parse dialect, and implish is very much inspired by Red and K, so it's like a blend of those two things. But I'm not looking at how they did things. I want to. Alan K, the Smalltalk guy, yeah. He funded he had it's called vpri.org, viewpoints research initiative.org, institute.org, viewpoints. And yeah, and after 16 years they were out of business. But I don't know what he was doing anymore, but they had a lot of interesting stuff on here. They were basically trying to build like a, basically how small could they get it from, how small could they make like a personal computing environment or whatever. But I don't know a lot about what they did here. Lots of interesting things came out, and there were like artifacts, but I don't know. I guess my approach to this kind of thing, it's small. The goal of Smalltalk and Alan Kay's goal in general, at least, is to encourage research by getting lots of smart people together and have them work on things. But I think, I could be completely wrong about this, but my understanding is that they're trying to make a system that's easy for a single person to understand and have in their head. He's still quite active on Quora, or at least was a few months ago. Very creative guy. I didn't know that. That's interesting. You can follow. I never really followed people on Quora. I just, every once in a while they come up. I don't really look that much. Quora. Okay. We'll probably find this answer and go to. I'll look at this later. I'm not a topic about that. But I guess, yeah, I've actually been dealing with this a lot. So like, as I've been talking about this, people have been coming up to me, and there's like so many projects like what I'm doing, where people are making their own little interpreters and their own little systems, and a lot of people are making things that are like, in my mind, way better than the industrial tools, but they're small, and they might be well documented, but they're still black boxes, and so people don't trust them and whatnot. And there's a really great paper called Design Principles Behind Smalltalk, which is probably on this page. No, it is not. It's by Dan Ingalls. And one of the things is, like, you have to be able to fit the whole thing in your head. If a system is to serve the creative spirit, it must be entirely comprehensible to a single individual. And I think almost no system is, including Smalltalk. Well, that's not true. It's just, you still have that problem of loading it into your head. And how long does it take to load it into your head? And if you don't approach it by leaving yourself a trail, that takes you step by step, then you're still gonna have the elephant problem where you're looking at, the 10 blind guys looking at or touching different parts of the elephant. One guy says it's a tree, and one guy says it's a hose, and one guy says it's in a sheet because he's got the ear or something. Somebody's got a tail and it's a little rope. And they're just seeing different pieces of it, and you got to see the whole system, which is the Gestalt word. I've been watching a ton of coding streams about building interpreters. I learned a great tool called QBE for building compiler backends, way smaller, simpler than LLVM. QBE. I don't know about QBE. What is QBE? QBE compiler backend. If you look at Project Oberon, I mean, like, sadly he died recently, but the guy that wrote Pascal, Niklaus Wirth, he made like a whole operating system. He made an FPGA. He made an interpret. He made his own CPU in Verilog, blasted it down to an FPGA that you can buy. Now he's got his own hardware, and he built a whole operating system and everything from it. And it's just like a whole computing environment, and all the source code is there. That's one of the nice things about simple languages like Lisp, and even assembly in its own way. You can build a tower of abstractions, but the core languages are small. Yeah, that's kind of what I'm doing here. So I plan, like this thing. You start with this little tiny virtual machine. I think it has, well, it's still up in the air, but like it's intended, you should be able to get started with only, like 20 something instructions, and then other instructions can be implemented in terms of those, or you can build them by hand, and then you can build a Lisp, or you can build a. I don't think I had the idea of Minnow formalized when I made this diagram, but this is what I'm working on right now, like this parser. So eTree is like a XML structure, tag, attributes, dictionary, and contents. Is simple in JavaScript. It's a little more complicated when you're building it on an assembly language, but then the point is to do exactly what I'm doing right now. You need a language for templates for output, and a language for the parser, and you need to be able to, interpret it. All right, so what I do with this, and this is sad, is I add this to things like to read, and then I never see it again. But it's in there, and then someday I'm going to go through and organize all those bookmarks. In fact, I have a tool to do that, to organize things. Right. I'm rambling. Okay, and then I'm gonna just ignore all those loops I just opened and just I want to make this. And I think if we go back here, like, I was looking at this one, but maybe this is just as nice. Well, we're gonna have a function called match. Or grammar interpreter. And we need like imp, match.imp. I'm just going to put it like this. Name match.imp. Why am I doing that? Begin source. And this is implish. I know it's actually whatever. We don't know what language this is. It's test. It's Tanko test input language. So first of all, I don't have a. Oh, I do. I do, don't I? True and false are going to be O and I. So O looks like a 0 and I looks like a 1. And those are the symbols I'm going to use for true and false. I guess you can also say true and on, whatever, but. So that should be I. Match imp 1, 2, 3. That should be I. So basically, imp should match everything. And what match is going to do, I should follow my own trail here, but match is going to do is it's going to take a grammar and it's going to take input or source. But in this case, it's going to be a token tree, so it's tokens. I've never actually done this before, like a tree. Tree. Or, oh yeah, like item. Imp, imp data. Imp item. Imp object. Imp X. I don't know. Just takes an imp. Imp data. And then it, it's going to make S is going to be state. I mean, that's not, I guess it's JavaScript. So let S equal state, new state, imp data. Let me refresh my memory how this works. I think I did it one way here. Let's just read this thing. This is 900 hours anyway, so. How about I read it in such a way that it's on the screen? Our goal is to bootstrap an interpreter for a new programming language. We'd like to build it incrementally from the ground up. Rather than writing parser by hand, we would like to model the language syntax and semantics as data and pass this data to a generic grammar interpreter. This is me writing. I'm reading myself from 800 years ago. Rather than writing a parser by hand, we would like to model the language. We will build this grammar interpreter incrementally with test cases. For starters, we will focus on simple regular expressions, much like Python's built-in regular expression module. Here we have a lit and a lit, and we make a matcher which has this state inside of it. So I wanted to match the literal x followed by literal y. We get this. And I think later in J, I call this CHR and CHR for a character or an element or something like that. And then lit was allowed to match like a whole string or token or something. All right, so we say now we have the matcher thing, and then we say matcher match, and then we get matcher fail. Here are our data types for modeling grammar definitions. Since we are using name tuple, there are no actual behavior associated with them. This is just, they're just constructors. Yeah, so they're just data, name tuples, which is what like the data syntax in implish is going to be. If you use curly braces, name curly brace, you get data rather than a function application. I mean, in either case, you get a tree with a tag at the top that says there's some delimiter, but we're going to interpret one as being, word bracket is going to be we're going to interpret that as a function call, and word curly brace is going to be like this, a chunk of data floating around. Then we named a bunch of things. These are just name tuples. So this is a type called gram, contains grammar rules, and then it has these arguments: name, bases, dot, body. Okay. Def, I don't know what bases is. A def has a name and a body. That's a named grammar rule. A ref is a reference to one of those rules. Any is match anything. Single item, single thing. Not. Right, skip. This is like a tree builder kind of thing. So this is probably a little bit out of space, out of place. Empty is the empty pattern. It always matches. Since it doesn't need arguments, we just refer to it directly. T for type. Oh, I see. A tag with an item, a tag with a body, a tag with a name. Tag. Blah, blah, blah. I see. So this is building a named. Creates a new tuple type. So it's a tuple with a body, a tuple with an item, a name, and okay, a name or body. That's what this is. Lit, string, sequence, group. So these are all defining new types. Renders in parentheses. Okay, that's silly. I guess that makes sense, yeah. These are like the core things. Maybe not group, but lit, character, string. Oh, I see. There's a string of literals. String of characters. Sequence is like patterns. We're composing the patterns together. Here you're composing characters. But we don't have these, right? Because we have a string, we have symbols. We have symbols in implish. We're parsing a list, not a string. But this is the same. So you have a sequence of something. You have alternate items for something. TB is for tags with unbound listed child nodes. TB, probably. Yeah. Just has a body. It has something called a body inside of it. Whereas a TI has one item in it. So like not is a pattern. So any, this T doesn't have any arguments whatsoever. And no arguments here. Because it just it's like the dot in a regular expression. I don't think not would be like a look ahead thing. Fail if you look ahead to see if it matches and then you don't consume. TB and TI, so let's just go through it then. TB, code review. Okay, so def T is we got a tag, a doc, and an args. And this is going to create a name tuple with tag and args. And then if there's a doc, we're going to add it to the res by assigning this doc thing in Python. So then if you look at the help, you can like if you ask for help on T, it'll say this string. Okay, so then TB is a function that takes tag. So I'll take a tag and the documentation, the name of the name tuple, the name of the type, and then the string, the doc string, and then the arguments for that thing. So this is basically just saying name tuple gram with this document, or name tuple with these args, gram and this, and then giving this the doc string. TB, yeah. So the body is intended. It's just giving a name to the thing. So that they're just a tuple of three things, or sorry, of one thing. It's a tuple containing a body, a field called body. This has a field called item. This has a field called name. So it's just a matter of what do I want to call the things. And yeah, I'm referring to TB would be a list of items, whereas item is going to be one thing, whereas B is going to be a list of patterns. That's just the whatever. So here you have a pattern to skip, or you have a pattern to look at, and then you say, well, I don't want that pattern. Here you match the pattern, but then you just ignore it. So if you want to like remove a token, like a separator or something like that, you don't actually need in the thing. Here's the empty thing, no arguments. Here's an item called a lit, so that you have to pass in the literal character. Here's this thing where you pass in a string. Here you would pass in a list of these patterns, right? We'll see some examples in a little bit. So the main group is, I don't even know why that's there, but that sequence and alt are the two main ones. This is the semicolon, and this is the well, actually, this is a semicolon in programming. In these grammars, you don't have them. And then alt is the pipe. So that's why these are the two separator characters. A grammar is generally, the end of each thing has a semicolon. And so you have a bunch of sequences, and then, each rule has a bunch of alternatives separated by pipe characters. And so alt is a list of sequences, and sequence is a list of patterns. Although I guess you could have just a single item in there. Rep is match one or more possibilities. Opt is match 0 or 1 repetitions. So it's optional. And then ORP is a combination of these two, which is optionally repeat. Yes, I'm trying to use like an algebraic data type in Python. You can actually make like data classes now. It's a little bit closer to. It's still building on name tuple, but name tuple is as close as you could get last time I touched this. Yes, these are constructors. So you say alts. And name tuple in Python just does that. So here's my REPL here. Python from named. Let's say IPython, right? Maybe. Or how about import name tuple? Name tuple? What is it? Oh, collections import name tuple. as nt. And you say like nt foo, and then 1, 2, 3. So now, does that exist? No. Yeah, I didn't think so. Foo? No. Right, you have to assign something. You say foo is this, and now you can say foo. No, I think you say 1. Trace. And there you go. And so you get a tuple, or you get the structure that's kind of like a little bit of a dictionary or whatever. But you can't then, so now you say ABC equals this, and you say ABC1 is equal to blah, blah, blah. Oh, you can't set it. Interesting. So it's a tuple, so it's immutable. That's interesting. The thing I'm using in Tenko is a new thing called a data class, and you can set them. So I was a little confused. But right, tuples are immutable. So there you go. That should say it doesn't even have a slot yet. Yeah, whatever. Anyway, that's that. So I just use that to make like a little data structure. And so yeah, so like in the example now we can just call lit, and you can say alt with a list of these things. So here's either X or Y. And then somewhere we have a thing that says how do we, okay, so wait, hang on. I'm not going to skip ahead. Since we will be composing instances of these types into trees, I'm such a bad student of my like I wrote this whole thing so I wouldn't have to remember this stuff, and I just keep skipping ahead rather than reading it. Yeah. Yeah, I really like name tuples. Name tuples have been around for a while, but I mean there's implementing again. Since we will be composing instances of these types into trees, and we want our system to interpret this thing of nested data structures that is just like whether they have strong typing or not, but like or static typing, like algebraic data types in Haskell are great for thinking about things, but just being able to express trees and documents like this so that you can have any language you want and write little interpreters and stuff is like the main reason I'm writing implish instead of just writing a K, right? Like I really want the nesting ability. And so that's why we're starting with that. And then embedding the array features inside of the tree stuff, like because with this you can have whatever language you want, and then if you happen to have a bunch of really powerful array primitives there, then I think that's nice. I think it'll be nice. I don't know, we'll see. All right, let's read it. We will implement this using a base class that simply maps each name tuple type to a method with the same name and a given prefix. Okay. In other words, when we see, so this is the thing that's going to match that. So when we see an alt node in the tree, we can use this to automatically invoke a method in our interpreter called match alt. Okay. So we tell it what prefix we want, we give it the thing, and then we dispatch prefix thing, and then that works. So how does it work? Well, we find a handler. So given a prefix and a name tuple, we get back a callable. This is before we had type annotation, so I had to put it in the comments here. So you get a prefix and a name tuple, and you get back a callable, which is one of the methods on this. So get self, look at yourself, and see if you have the prefix followed by the node type of the node, which is the class name. So whatever this is, so it'll be alt if you're passed in an alt. And so we inspect the tuple and figure out what type it is, or what the tag is, and then we build the name of it. As it said, alt with the prefix match becomes match alt. That's this line, this part right here, and then as a default to the get attr, we say self unhandled, which is this. No handler found, blah, blah, blah. So we find that, that's called H now. We call H and we pass in the node with the arguments that are, and the keyword arguments that are passed to dispatch. So we say dispatch prefix, no, match the value and then whatever arguments we want to pass into it. Okay. We also need to keep track of where we are in the input sequence. The following helper class will do the work for us. We have a cursor, we have a sequence, probably a string, but now it's not a string anymore. The value is none. This is like almost exactly right. So I call it an implish, right? So we have in the evaluator, the current evaluator that I'm going to replace now. I started doing this kind of stuff here. So we have here is the list that you're working through because now it's nested, right? So we have to do a little bit more. We have the position, and the current item is called item instead of value or whatever. But like this same kind of thing. So then self forward is immediately we start at -1. We're going to immediately go to the next token. So this is like get the next thing out of the list. I think in implish I called next item. And it's slightly different because we have to do special things based on different kinds of symbols. But everything else is just an item. So if it's a symbol, we do special things like, I don't know, to prevent it from, there's special syntax to prevent a word from executing in these logo rebel style languages. But I might change some of this a bit. Anyway, yeah, this is get the next item and update these variables. Then are we at the end? And I even have an at end. So this is very common thinking for me. Data structures for parse results matching should either produce a match object, okay, or a special constant called fail. So this has a text and a position. I don't know why we have the position in here. We're also going to use a name tuple to represent the match state at any given time. The state includes the match result, a cursor marking the position in the string, and an environment which we will use later on. Oh, you need this. You need the position plus the length to find out. Like, I mean, that's just how you're tracking things. So, because you're moving ahead, if you want to backtrack, you have to go back to that position and so on. Okay, so does the cursor have a backtracking thing? No, we just remember the position of the cursor. Because again, we're just walking through a string. It's a flat sequence. Whereas in implish, I'm walking through a tree, so it's different. So the concept is the same. You also have to recurse into them. We are also going to use the name tuple to represent the match. Yeah, that's where I'm at. So did it match or not is just based on whether the value is fail or not. So we have a value, a cursor, and an environment. In which we will later on for storing state, yes. Simple pattern matching. I'm pretty sure I did this pretty much the same way in J, except it's a boxed list. Simple pattern matching. Now we can start building the matcher. First, we will set up the dispatch stuff. Simple matcher for regular languages. This is a class, and it's based on that dispatcher, and we're going to give it a prefix. So when we say match, we're going to call dispatch match with these things. Pass in the state class, the M class. And returns a match state tuple. It returns an, oh wait. We give it the node, the grammar, the cursor, which is wrapping the string and giving a position on a string, right? So we have the sequence, it remembers the sequence. That's our input. Okay. And so this can move back and forth on there. And then we have an environment, which is, again, just an empty dictionary right now. Or we don't know what it is yet, but it's probably going to be an empty. So when we create a matcher, we give it the grammar. And then when we say match, we create a cursor on the input. We get the input, we create a cursor on that input. Yes, here's our empty dictionary. And then we run match with those things. And then when we get back the value. It'd be nice to have type annotations. This is a literate program, so this is org mode allows you to add things that later get generated. So when you untangle this thing, this generates a Python file. And so this is just a slot to put something in. It's not Python, it's org mode syntax. Now we are ready to implement the handlers for our initial example. The simplest case is comparison against a single literal character, yes. Probably the empty case is a simpler, because empty matches everything and just doesn't consume anything. But it returns an M, which is a tuple, is a state. I think this part, it returns it returns the part that we matched, right? Yes, so we give it input that has X, Y, and Z in it. We tell it to match one of these two characters, and it matches X first, so it returns the token that we matched, the thing we matched. And ignores this for now. So a long time ago, you asked, how does it know if it reaches the end? So it says to match X or Y as it matches X, and then Y and Z are just there, and it just ignores the rest of it because that's not part of the grammar. Since we will be composing instances of these types into trees. Oh, I've already. Okay, so all the stuff that we've done now, we should now be able to say match a literal, and it should match or not. Oh, and if we match alt, then we can actually say this. We can make this example work at this point. So all we have to do to implement X or Y is translate this nonsense into implish. This is all like Python. You don't need all this. You just need, right? So without going any further, I want to get this example working in implish. So I need well, let's call this the sequence. That's the cursor. So like, let's see. Doesn't we want the sequence, we want the environment, and then like other stuff. I guess the environment can be whatever we want. Position. Is that what I said? Or I guess we have a cursor. Right? Is each rule responsible for manually advancing the cursor as it consumes tokens? Well, yes, so it manually, this one does. But so alt matches each one of those for each of my alternatives. I didn't even read this, did I? I said I wasn't going to skip ahead, and I didn't read it. Let's read these two. So inside of matcher, this is again being filled in at this slot right here. You can't see the annotations here, but if you looked at the raw thing, it would say to put that here. So inside this class, we're going to say matchlet self node cursor environment. So it's a method on this class. Have a node cursor and environment because those are that's how dispatch works. Okay. We're going to return a new M, which is this class right here. It has a value, a cursor, and an environment. Okay. So this is the value. So we return a match or a fail. We return a match if the current value is, so the current val has got to be like a property on cursor. No, yeah, so it's property there. So if the current value is equal to the item here. So node here would be like the word lit. This would be the lit with X inside of it. So this would be the item would be X. So else we return a fail with the environment. And the idea is that we return this is so we can do backtracking when we get to alt. Okay, so we current environment, cursor and environment. And we say, okay, the cursor is pointing at something. If it matches, we're going to move the cursor forward, which should return itself, right? Yeah, return self. That way we can move it forward and get that's the next cursor. Yeah, that was my exact question. Assuming cur forward moves a copy cursor incremented, but it doesn't make a copy. That's why I was scrolling up here to see like move forward in the sequence and return the next item. Well, it doesn't return the next item. It points val at the next item. When I did this in J, it was completely. I have a state tuple, like an array of boxes, and then the position. It copies that and changes the position, so it absolutely makes a copy. And then if you want to backtrack, you just throw away the new copy and you look at the old copy. So I must have to go backwards somehow. Oh, well, maybe this is just a bug. Maybe this just doesn't work because you're right. This should return it. This should make a copy, or otherwise it's mutating the thing in place. Maybe. I mean, this worked. This was not like just making stuff up. I ran this code and it worked. Go ahead. I gotta be missing something because this totally worked. I've written this many times. Ah, okay, so here we do. Maybe. I didn't just make this up. This works. But maybe I only parse things that match, and so there's never any backtracking. But this is the same kind of thing we're going to do. Like whether this works or not, like the idea is right. And so I should be able to take this and paste this into or translate this into whatever syntax we come up with, which is probably going to be tomorrow now at this point. I think what I'm going to do is I'm going to read this. I'm going to read the J thing, and then think about this tonight, and then come back tomorrow when I'm fresh and like do this again, like actually implement it. Because like I sat down to do this and like I haven't thought about this in like parsing in ages. I mean, I guess I've been thinking about parsing all week because I've been writing a parser by hand, but like this idea of writing the grammar interpreter, um, a little more harder than just writing the parser directly. But yeah, okay, hang on. This is why. This is why. So we're talking about backtracking now. I should have mentioned. Okay, so this is confusing because yeah. So the matcher had a bug, but this is right. Where does it do it? It has to be in one of the things for alt. So this is the only thing. This is where it should be. It should absolutely do that. This should not. I have no explanation for this. Why? How could this have worked? Unless I just didn't run into any. I kept the example so simple that I didn't. I didn't require it to backtrack, which is entirely possible. Because like at the time that I wrote this, I knew how to do it, and so I just did a bug, and I didn't make the tests good enough to find a bug. Oh wait, hang on. No. Yeah, this is acting as if it. No. Yeah, the only place it's ever going to backtrack is with opt, which is optional, but that is written in terms of alt. Like so alt is the only place you should ever have to do that, and it should roll back your changes. Or, as you said, forward should Yeah, I think this is just a bug. All right, let's look at the J version. Because I know the J version works. So this is at, it's probably already in a direct, it's right there. This is in Cinder, tangents from Cinder, parsecode.ijs. I know I didn't finish reading that. Maybe I should finish reading it. And not, let's do what I said I was going to do and just finish reading it. So input cursor, we talked about that. Data structure for parse results, we talked about that. Pattern matching. Regular expressions with lit and all out of the way. Only a few more cases need to follow. Allow full. Okay, so let's just imagine that this is functional and this returned a copy of the cursor, which is what it should do. Might need slightly different, whatever. Right, so emp matches the empty string and takes no arguments and always succeeds. Yep, great. Sequence takes the list of patterns and matches all of them in sequence. A, B, A, and then either an A or a B. We definitely have to backtrack here. Maybe I changed this and this no longer works, but that seems wrong. Yeah, I think this does back. Okay, but this doesn't match, so this never triggers. Yeah, so I just don't have a complicated enough example that requires backtracking more than one token. So if you only have to look ahead one step, then we just dispatcher does not make a copy of anything. Dispatcher is just the Python thing up here that a dispatcher is just doing this nonsense to like match the type of node to a method name. So does the work of matching the word alt and the prefix match and giving the node alt and binding them to this method name and then finding that method. That's what dispatch is doing. That's what self dispatch is doing. So it's creating so self dispatch with match is creating match underscore alt. So nothing makes a copy, but it's just my test is not sophisticated enough to catch this error because or my examples are not, because like here, well, you're looking at the next you're looking at a all right, so here we match A. Great. So now we're looking at B. Right? So that's what her value is. Her value is the string B or the letter B. And it says, well, okay, if the current value is A, then we move the thing forward. Okay, but it's not, so we don't move it forward. Yeah, this only exposes a bug. Like if we were comparing like A, B, or like, AA versus AB, lit AA versus lit BB, lit AB, then we would match the A, and then, or I guess it would have to be a sequence in this case. So we're only matching one character at a time. right? But like if you have to match two things in order for this to be a bug, because the first thing matches, that's fine. You know, if it doesn't match, you're just looking at that one character and you don't have to backtrack. You just don't move forward in the first place. But if we match two characters, this whole system would break because that's not functional. And the fix would just be to do it the right way and make this return a copy instead of returning self. It should be possible to construct a test case that passes in the J version but fails in the Python one and soon passes in the implish version. Yes. But we would have to copy that test and rewrite it 3 times unless you had a language for talking to your test, which is why I like to have a testing framework that sends these things. That's again why the syntax is there in the first place. So you ought to be able to send the same abstract grammar to any of the languages, and then it doesn't matter how you implement it internally, but if you can parse the grammar and build the structures, then you know, then it would be able to test things. So you can't write one test for 3 different languages unless you have a system like this, about like what I'm building, right? So, but yes, in principle, you could write that the example and then test it in all 3. All right. Anyway, so let's just assume that that bug is not here and just keep reading the idea. So, right. So I said I was going to stop here, but then I said let's go ahead. Okay. So it was lit and out of the way. Let's match a single character, and then alternatives. We only need a few more cases to allow full regular expressions. And I think, did I say sequence as well? No, I haven't done sequence. All right. So empty string, no arguments, and always succeeds. So that would be like caret $sign as a regular expression. Well, no, not really, because you can put that anywhere. I forget what this is. Actually, this would be more like the use. This is how you implement optional. It's alt and empty. So alt and then a sequence. So alt with either a sequence or empty allows you to say. Well, you'll see it in a second here. Oh, okay. So these are test cases. These are like doc strings. So this matches. This matches. Here we have sequence, takes a list of patterns and matches them in sequence. This is just, these are like laying out what the spec should be. So this is like what the language should be. So string matches a string of literals. I think I called it something slightly different in J. Rep matches 1 or more repetitions of a pattern. Rep is definitely the same name. Okay, so match A, and it should match those 3, which it does. Okay. According to this, opt indicates that it matches optional, and it's equivalent to alt with the X. Opt X is equivalent to alt X or the empty. It works like the question mark in regular expressions. So match opt A and then ABC matches correct, and then match the same thing against XYZ, and it gets you that. Oh, hang on. Excuse me. Oh, I thought maybe we'd make a new cursor somewhere, but no, we don't. Nothing ever makes a new cursor except right here. So I thought maybe the match function itself would do that, but no. Underscore match is what we call. So that you never call that top level match. Because here it's making a new cursor, but in these implementations it does not. Oh, so we skipped ahead. All right, and then opt is alt or emp, okay, and then orp is shorthand for opt and rep, and works like a the Claney star. Claney. M is matcher, orp lit a, okay. Work. If you prefer, you could treat orp as the more primitive operation and rep as the sugar for sequence orp. But if you prefer, you could treat the star as the more primitive or the Claney star as the Claney star as the more primitive operation and rep as sugar. So the Claney plus sugar for an X, one of them followed by any number of them. So match empty matches an empty string at the current position. Boom. Okay. Now moving forward. So lit is the only place that moves forward. So that's the only place that bug exists. Join match results. Okay, blah, blah, blah. If it matches, return fail. Otherwise, pick all the text of all the matches that we have. Okay. For sequence and string. Okay. The sequence, the string is specifically, I see. So I made matching a string, just do a bunch of literals. And J, that was much easier. So that became like a primitive. And then literal just went away. But yeah, so we'll match one literal character, and then a string would allow you to match a bunch of characters in a row. So it's just like sequence, but wrapping everything in a lit, every character in a lit. It takes a string or whatever. Or it takes a string node. Match sequence. Right, for item in node body, if it matches, blah blah blah. Or if it matches, so first of all, check see if it, yeah. If it's fail, then we failed, and we fail the whole thing. This would be backtrack. This is where you would backtrack. So you want to return the original thing, right? This is where yeah. So res equals self underscore match. So you never made a new copy of it. You never made a new cursor. You never cloned anything. So yeah, it's still a bug. Okay. But anyway, if it fails, return the failure. Otherwise, and this should be like the original position, right? That's the intent. And then otherwise you append some values and so on. So, okay. And then return the match. Match rep, self node, cur environment, vals while true, res equals self match, node item, cur environment. If res val, fail break, else, blah, blah, blah. What is it saying? We're going to match repetitions of it. So we need to collect a bunch of repetitions. So while it's true until we break out of this, you match. And if you fail, that's not failing the whole thing. It only fails if vals winds up being empty. So, but you never match anything, then you fail. So vals or fail. Is it optional? Then you just say, well, again, we just construct a new node on the fly. It takes the item and match it. Okay, so then optional, the same thing. You just construct a new node on the fly using opt and rep. Optionally repeat this. Okay, most modern regular expression engines support additions like groups and back references. We will diverge a bit here though because we are interested and we're writing full parsers with mutually recursive named rules. While not strictly required as a traditional breakup parsing into two phases, the first, yeah, so this peg systems do not require a lexer and a parser. They don't require it, but I like it anyway because you want to like colorize your code and things like that. In which case you only need the lexer. You just want to be able to get a stream of tokens. First pass scans through the text and breaks it up into tokens, a process called tokenization or lexing. The second pass parses a stream of tokens and, excuse me, at least conceptually, constructs a tree-like structure. Our version of tokens will just be tuples, strings tagged with tuples, comma, strings, tagged with rule names and match positions, okay? So tokens will just be is this the pattern? So we scan this, we scan A. Tagged with rule names and path. So this seems weird. So this is what we matched. This is the rule name. A little weird. This is what we matched. This is the rule name. This is what we matched, and then position. Okay. Later on, we can improve the performance by compiling blah 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 into a state machine, but we will stick with something simple where we're bootstrapping the rest of the system. So here's the scanner that's going to do this thing for us. So we give it a list of regular expressions. Like, yeah, so we give it a list of things that we might want to match, and then this is going to tell us which tokens are they. So we give it a token, like the class name, and then the whatever token type, and then like this would be like integer, and this is how you match an integer, and so on. The rules are string, tuple. Okay. Test the rules in a given order. Okay. So rules. So we didn't have at the time dictionaries did not go in the right or didn't remember their order. So if you wanted to make a thing in order, you had to explicitly track. Python now keeps track of the order, and if you the order in which you insert things into a dictionary is the order that you can traverse that dictionary and get them back out. That was not the case before because of the way it hashed things. It just read the hash table. Default whitespace handler, if underscore is not in the rules. Oh, that's our name for the underscore. So at the very start, we're going to add a rule for underscore that gives you whitespace in range 33. So anything under all the whitespace characters, basically. Anything space and related. So yeah, new lines and all that stuff would be whitespace. All right, so then that's we pass it some rules, and now we have a bunch of rules in a particular order, and then gen tokens. Given a text, we create a cursor, create a matcher. Oh, I see. But we ignore it rather than keeping its own grammar its own grammar node rule every time. We just pass in a new rule every time. So this is kind of silly. Well, I guess it's useful for earlier on. All right. Anyway, if it matched, we do that. Otherwise, we go on to the next rule and so on. So we just keep we just match until we get a token. Loop through all the rules until we get a token, and then we consume it, and then we keep doing that until we're at the end of the thing, and that's our tokenizer. Okay. And then we just scan is just returning a list of those. We're about to extend the simple string matcher into a full parsing system. One thing we would like to be able to parse is a nicer syntax for building grammar. So like, yeah, immediately after you build this thing, then you want to write your parsing engine. So you write this grammar. We use EBNF, which is extended back as NAR. Here's a grammar for eBNF, written in eBNF so we can test the parser. I think I took this right out of compiler construction. Yeah. It's adapted from compiler construction by Niklas Wirth, who invented eBNF, as well as Pascal, Modula, Oberon, and a variety of other languages. Yeah, so he, instead of, so this I think is, yeah, it's self-describing. The curly brace syntax corresponds to ORP sequence, optionally repeat in our world. The pipe is placed between alternatives, and the characters in quotes correspond to lit. So this is a grammar describing this grammar. The main is a list of any number of rules, and then the end. A rule is an identifier is equal to this. So here is a rule named rule, and the ident is rule, and then the equal sign is that equal sign, and then the expression is this part right here, and then the dot is this dot right here. So this is the rule for describing a rule. And then expression is a rule that has a term followed by, so this expands to this, a term followed by any number of pipe characters and then more terms. A term is a factor followed by factors. So this is, there's no separator here. This is just space separated factors. He kind of modeled it after a polynomial or something. These are all the things you multiply together. The sequence is the multiplication, and alternate is the plus. It seems a little backwards to me, but okay, whatever. No, that's right. That's a multiplication. That's why they call it an algebraic data type, right? So because a factor multiplies the number of things. So if you have the letters A and B and C, you have 3 options here, and then you have 3 options here. So you're multiplying 3 by 3. So you have 9 possible options for the 2 things. Whereas if you have 3 here, 3 options here, and 3 options here, well, you pick one of those 3, and then you pick one of these 3. And they're just more alternatives. So you just added, you've now got 6 alternatives. So these alternatives or these alternatives. And you don't have both of them. So this is an addition, and this is a multiplication, and that's exactly like a polynomial. So it's an algebraic data type. Okay. Ident string, blah, 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 blah. And then this is a grouping construct, okay. Which is not actually used in this example. And presumably ident and string are defined elsewhere. All right. So it is self-describing. The curly braces corresponds to ORP of a sequence. So here's a sequence. They use a star in product types. I've used OCaml or OCaml, whatever. OCaml. It's French, right? OCaml. I don't know. I've used it once or twice, but I haven't really written much in it. I think it looks like a really nice language. But I didn't notice that they use a star for product types. Oh, wait. Yeah, they do, don't they? Yeah. Yeah, I'm not necessarily explaining this to you. I'm just explaining this to anybody watching or myself or, whatever. I just ramble sometimes. As you probably know. This definition is adapted from compiler construction. And blah, blah, blah. Okay, so brackets define the factor isn't actually used by the grammar, but it corresponds to the opt. Isn't actually used by this grammar. Yes, okay. The syntax corresponds to seeks. These, of course, be nested inside of each other to arbitrary depths. It actually corresponds to group, right? The lowercase names correspond to rule definitions and references to those rules. Lowercase are rules, cap uppers are tokens, right? our terminals, terminal tokens. Yeah, okay. Yeah. The appeal of OCaml to me is that it's strict, eager. It eagerly evaluates things. So you, or I think, right? It's not lazy like Haskell. Haskell's such a lazy language. You get off its ass. Um, but um, no, I guess I don't know that that's a bad thing. I just found it interesting. I kind of liked it. But um, whenever I try to use OCaml, I'm on Windows, even though I have. It bothers me that it's not easy to get it running on Windows, and I think they're working on that. But every time I've tried it, like I don't know why, because I run everything under a shell most of the time anyway. But whatever. But also because of Lean. Lean 4 is just it's a research language, and it, like, a lot of mathematicians are really interested in it, and it has it's not the Hindley Miller. I don't know. Milner? I don't know, whatever. But it's not the same. It's got a richer language. It's got dependent types, type language, so you can do like proofs in the type system, and it's also got like a parsing system to plug in new grammars and whatnot. And so basically, I saw Lean 4 and I was like, oh, I'll just learn this, and it's not as people aren't as excited about it, but I think it's a really, really interesting language. Milner, yeah. He's the guy that made ML, right? I don't know. I don't know who Hindley is. Anyway. I'm trying to read this. I just want to load this into my head. It's like 12:30 here. I got to go to bed. That's part of why I'm rambling here. The uppercase names refer to token types. I place the definition code in a block of its. I'm not even going to get to the J thing tonight. I place the definition code in a block of its own, so it should be syntax highlight, but for Python, it should be inside of a string. Okay, that makes sense. Our next major goal will be to parse grammars like these. First, we will manually create a tokenizer for the language, and then we will extend the matcher with def and ref and the ability to match tokens rather than just strings. Then we will manually translate the above EBNF definition into a data structure built that doesn't make any sense, that we can pass to the grammar interpreter. Probably built so that we can. Okay, so we translate these rules. Main equals rule. There's no main. So these are escape character, single quote, double quote, letter equals any of these letters. String character equals either a sequence of an escape character and then another escape character or a double quote. So you can escape the double quote, or you can escape the escape, or any of the characters in this range, which is 32 is a space and everything up. These are the printable ASCII characters if it isn't a double quote or the backslash character. Okay. And then the scanner. All right, so that's not these rules. That's just the scanning this. So everything. Okay, so that's fine. So a string is a double quote and a string character. Right, so that's what that's for. I should have read this from the bottom. The identifier is a bunch of letters, and a string is quoted, and then any of these characters can be a token. So we're making a rule for each one. So we say, this is the rule, and it has the literal character this in it. And then those are all the first rules for these individual tokens. And then we have a rule for ident, and then we have a rule for this. So we add these two list of these things, and then this together. Here's how to use it. Scan this, and we get back this. I believe that works. I trust it. Because I did not write this by hand. That's why I trust it. Parsing. We parse recursive grammars, but I believe it fails for the reasons we talked about. The parse recursive grammars where patterns can be nested inside each other to arbitrary depths. There's not too much more we need to do. We just need to supply our interpreter with a bunch of named rules and then be able to tell it, which we have named rules already, but then we need to tell it when to match those rules. We need a way to match the rule and descend. Okay, so unlike a scanner where the choice of pattern that gets matched depends on the input, as if each pattern were a child of an alt. Right, so as if you had an alt of all the patterns, right? The parser starts with the top level rule that it attempts to match and follows references to other rules only when they appear in the patterns. Right. So tokenizer says, here's a bunch of things that can be there, figure out what they are. Just go through all of them in order, I guess. Whereas parser is guided. Okay, named rules. For our purposes, a parser is just a generic matcher that adds named rules that can refer to each other recursively and which operates on a stream of tokens rather than just a string. Okay, so we are, no, that's just, it's still a linear stream of tokens. Therefore, we are going to subclass matcher. However, rather than adding support for def and ref only in the subclass, I'm going to push them up to matcher. That way, matcher will have support for named rules matching on strings, and the only difference we'll see in parser is that it operates on tokens. And that way you can, instead of just a regular expression, you can do what we did in here where we said we have tokens that call named rules. Okay, great. Presumably we're adding this one line. Doesn't say what it is, but I presume that's the... Okay. Now we can create and refer to rules. And we... Oh, so then we keep a dictionary of defs, and so when we see a def, we just add it to the rule. Add it to the dictionary. Right, and so a definition is just when we read the definition, that's a little weird. I wouldn't call this a match, but so because it's not a match, I just told it to match empty. Okay, so. Huh. Okay, but the ref makes more sense because the ref is actually something you would match, but you wouldn't match a definition. Oh, I see. I guess, okay, so we just put it in a sequence here. That's interesting. So the sequence is first we define something, and then, so it's as if we had like in our regular expression, we had like just a syntax. Okay, I guess that makes sense. We just had like an escape sequence that says, okay, here's a named rule and here's how you define it, but don't match anything. So it's just treated as a, just yeah, whatever. It does not consume any input, right? Which is exactly what emp does. Match ref. So now, okay, so the sequence is this, which matches, which is like the empty thing. It just ignored. As far as the parsing is concerned, it just mutates the state, or it just defines something. And then ref allows you to look at that rule, and so then we find the rule out of our dictionary, and then we match it, and there you go. Now the parser class can just focus on the work of turning a stream of tokens into a tree. One of the main differences is that we are now operating on tokens. This means we have lit match a token rather than a character, and therefore we no longer have to have any need for string. Okay. However, there are two ways you might want to match a token. By its content, for example, a literal keyword like Python's def, or by its kind, for example, any string. We will continue to use lit for an exact match on the content and introduce toke for a match on the token type. Further, we need to override join so that we can build nested lists of tokens rather than simply concatenating strings. So in parser, we change lit to do what? Match token based on its content. And again, we have that mistake. If current value and current value 0 equals n, oh, no, equals node that item, else fail, okay. So a token has a content and a type, and so we match on its type. That's interesting, because I actually wanted to do the same kind of thing. I want to be able to say, if it's a noun, yo, it's 5 a.m. here, yes. Looks like start up stuff to do before going to bed. Well, have fun. Thanks for hanging out. I'm going to just keep going ahead. Have a good night. Or have a good morning, I guess, at this point. Match tokes. Match string. Type error. String needs those make no sense in a grammar. Consider lit, toke, or seek. Okay, so that's an error. Helper to join match results for sequence. Seek always gives 5 a.m. man. Thank you. See you later. Thanks for hanging out. Helper to join match results for seek. Seek already gives us either fail or list. So really we're just turning off the filter that matcher used. However, so. Yeah, even I'm getting a little. I'm gonna make a video of this. Like there's been like this was meant to be the script of a video at some point, and that taking years, but it's gonna get there. So match this ugly stuff, get this, and now we find the thing. Bunch of definitions, and then we just match repetition of rules. We can get rid of some of the clutter in our grammar definition by allowing Python string. I guess this is so. So here's this rule. Rule A or rule C equals rule A. So C is an ident, and then it's that's token rule A or yeah. I like this. You really want to see this in action, like step by step, little pieces working together. I think the J REPL will do that. Adding one more handler lets us wrap the grammar definition in a nice wrapper object with special support for a main rule. That's actually way nicer. Why is it? Not really. It's the same. It just looks nice. It's nicer than that. This is ugly. All right. The idea here is to manually construct a data structure. So these trees can get messy, so we'll stick with a simple syntax for this round and then use that to implement something better. I think this is, as it says, clean up below here. These are like rough drafts of the same thing. Or base grammar to provide generic tokenization. So these are some patterns that are like, okay. And worlds for backtracking. A world is a context for holding changes. Similar to a working copy in a version control system. Yeah, so we roll back. I'd use the same thing for JPrez. I really like this concept. You just have chains of dictionaries that refer to each other. So prototype based kind of thing. So you just go override get attr and get item. So they delegate to a prototype object when there's no local value defined. And so now you can have like nested inheritance or whatever from different dictionaries, prototype based inheritance. Yep. This is really nice for backtracking because it makes a copy change, right? We'll assume now that we have the entire string in memory, and what doesn't make a copy, it makes a new world that has a link in the chain, right? So proto is whatever, and then gives it a prototype, and then yeah, so this is when there is no local, if it doesn't have its own copy of the attribute, it's a dictionary and it doesn't have its own attribute, then it calls, checks the prototype one, which is home, which is this empty dictionary. Same thing for get item. We'll assume for now that we have the entire string in memory. Okay. Line, page, column. Okay. Now we can put the whole thing together. Here's what we get. No handler. And our job is to go back and fill in the handler method for each node until we're able to walk the whole tree. These are translated from the sequent notation. Right, so these are the ones that were missing. No. Knit gram. I'm not sure what's going on here. Oh, here we go. We have to put all these things in. Yeah, so this was just like scraps of stuff left over. Okay, so this is the same kind of thing, but in J. And I plan to make a video about this. It'd be really nice. This is very cryptic, and my brain is not ready for this at this hour of the night. This is I and O. I think I mentioned earlier in the stream, I like to use I for true and O for false. This is a function that returns a match. So it's I as a function here. So if not match bit of the state, which is I think evaluate this train. Yeah, because we're composing functions in this version. I'm not going to go over this tonight. This is I'm very happy with this code in terms of like the mathematical construct of it, but it is like reading math, right? It's got a test suite and it's got all that stuff. This is very useful code, but I need to, you know, I got to explain it to myself. Basically, this is the state, and these are the members of the state to match bit the current index, current character. You need this as a reference on the screen, like as you're working, right? To understand the code. That's the trick of doing it tersely like this. It's like very easy to read. It's very mathematical. You can test correctness in your head, but you need a key on the screen. You have this open in a separate window or next to each other or whatever, side by side. Or just get used to it, load it into your head like it's not that big. When it's fresh in your mind, it makes sense. Tree builder, tree state, input buffer. So this is for like yeah, it's interesting. The Ledger one didn't have emit, did it? No. So the part. I kind of glazed over where we're actually building a nested dictionary or whatever. This is just a scan. This is not a deeply nested structure. Oh no, we scan it and then we match it. So where's matching working? Oh, because it just makes a list of whatever. The sequence itself makes a list. So the sequence way up here makes a list. Vowels, append. So that's the list. Vowels, there's the list and there's it's appending to it. Whereas in the in the J version, I use this tree builder concept where I use the word node, which is this line right here. This creates a new dictionary, and I do this in the implish as well. Emit would be this, and then at the end, well, because this is only being done inside of a sequence, when you get to the end of the sequence, then the call stack causes this to be done. So it's implicit. Whereas in the other versions, the J version and the other one, the JavaScript version, the implish version, I'm using these things node. So node is, yeah, create a node, start a new node in the tree with tag X. So they, and also I'm building like an XML kind of structure. So we have a head, a tag, and attributes. So you can set the, you can take a token and push it up to be the tag. And then you can set an adder to something, attribute to something. So this is, it's a little weird and ugly and stuff, but then you define a bunch of things, and then so here's a J string, right? It's, you know, squall. What's squall? Single quote and a literal. Okay. Oh, single quote and then single literal quote literal. So squo is just the string, and then actually make it a literal. I use like a adverbs in J to do this, like decorate each other. That's interesting. It's like a concatenative syntax here inside of J by using adverbs. So string escape is this, does this, and that's a sequence. Where is sequence defined? This was a choice. Like I didn't have to do it this way. Ah, see, it says M. So it's an adverb. So M sequence gives you back a function, right? Because you have to. It has to be because you need yeah, of course. You take some data and then you give it an adverb, and that's the only way you can create a function or a verb in J. You can't create a verb from a verb. You have to use an adverb. Create a verb. So, or I guess an adjective in this case to take a noun called M, and then you modify it. So that makes perfect sense. So you get this like trailing kind of thing. And the word on is running the parser. So here's an example. A lit rep on AA, that should pass. AB is either A or B. ABC, AB is a sequence. Oh, sorry, AB is A literal and the B literal. Sequence on AB cat, and that should work. C literal on cat. 1. Optional on cat. Oops. This is actually really nice. Like I should have started with this one. And done it in the prompt. I think what I'm going to do is tomorrow I'm going to go through this one. Like again, this, and maybe I'll take some notes. I might even do this off camera because I do want to. It doesn't matter. Nobody watches these streams. If you're watching this, I salute you. I suspect, like most people, you're just skipping through it because, like, that's what I would do. But maybe in the future, an AI will watch this thing for me and edit it into little pieces and extract interesting bits of it. Like, that was an interesting walk through this thing, but I mean, it's a, you know, far from being a good video. That's why I have this channel. I don't try to make good videos on this channel. I just try to get through stuff, and people want to watch, they watch. And if they don't, they don't. And that's fine with me either way, because I'm doing this for myself, and that's that. But someday there will be a video about this, and probably someday soon, like a real video, like a edited video about this. This is going to become a script. It's probably going to be out 3 videos: regular expressions, parsing, and then tree building. Because you can parse and just match the thing without building a tree or doing anything with it. Useful test case, because you got in J syntax you have double quotes. Sally O'Malley. So high is a rule. If it was nice in J, you could just define rules, right? I don't think you have to say def. No, but I think you do have to say ref. No? No, you don't have to say ref. You just use the rule. And these are functions, and you compose them, and you just, yeah. This is not building it. Well, it is building a data structure, but it's just quite different in J. This is a really nice piece of J code, as far as I'm concerned. Like I'm very, very happy with this J code. It's very cryptic and mathematical, but it's very terse. But you can understand it with a key, and then now you've got this very terse notation for doing things, and I think it's really nice. Like I think it'd make an interesting video on its own, even if I'm porting it to implish, right? I'm probably not going to use this much myself. I think it's a good video, and people who are interested in J will like it, and people who are interested in learning about J might like it, and so on. But I'm not going to read this whole thing tonight, so I'm going to just stop here, because I can tell I'm rambling and just drifting off into nowhere. So thanks for watching. If you watched this, thanks everybody, Batlin, and especially who came out. Anybody else who's hanging out here. It says nobody was watching the whole time, but obviously people were talking to me, so yeah, can't always be a good one. And yes, I will get back to implish, right? The whole point is to make implish, but I want to build what we're just doing as the core of implish. That's good. I'm lifting this up into the language layer. I could have bootstrapped it from J. I don't know. I've been wondering how to get this into the B4 VM world. And I think just doing it at the high level rather than trying to do it on the low level virtual machine is probably the way to go for now. And in the future, I'll figure out how to get this all the way down to the virtual machine. Like how to get this into assembly language and how to do it the right way. Not the right way, but how to do it this way. How to do it in an interesting way. But you know, whatever. I'm just rambling. It's 1 o'clock in the morning. It's actually 1:01 in the morning. So that's enough for me. And thanks for watching. I'll see you again soon. Bye. Adios.